Okay, just give me a. So is the panel also visible or it's not?
Visible, sir.
Visible, panel visible.
Okay, so I'm trying to remove this so that it doesn't come into the middle of the screen. Is this fine now? So if I make it full screen, does it show as a full screen?
No, sir.
Now?
It is okay now. Full screen.
Okay. Okay, this is good. Okay, thank you. Yeah. So today I'll take a little bit different course in the IoT based systems. Today I'll talk more about drones and how this upcoming technology like these UAVs or drones are serving as on-demand infrastructure for the next generation wireless networks, right? So this is a new area that is coming up in the drone-based in IoT systems, where we are trying to repurpose these unmanned aerial vehicles or drones as an on-demand vehicle for doing a lot of the sensing as well as networking stuff, right? And today I'll try to give you one sort of area where drones could be useful, and that is how to use this IoT-based systems or drones in disaster scenarios. And we are all aware of scenarios like this, like wildfires or tsunamis, earthquakes, and floods, and so on. And it's pretty common. We have these situations in India quite often, right? And once we have these situations, there are two main problems that arise. Okay, so one of the problem is we don't have mobile networks because that infrastructure is often destroyed, or in the village areas sometimes they are not present. Like they are very little bit of communication infrastructure is present, so it is very difficult for search and rescue people to go there and do the rescue operations, find the victims out, and so on, right? So, and another problem that we have in such situations is the lack of access to locations of the victims or the search responders, right? The first responders. So when they go and try to search in these kind of regions, these accidents or these places are often indoors, or they are under debris, or guarded by a lot of foliage and so on, so that they don't have access to GPS signals. And this also makes the problem of the search responders more severe. So you don't have access to location coordinates, and you don't have access to the wireless network that would have been made, that would have made the task of the first responders much easier to some extent, right? So what I call this is disconnected by disaster, right? And we are trying to see what options exist today by using drones, so that we can restore this network to a certain extent, or use IoT-based sensing to get an idea of the location coordinates of the victims inside the buildings or under the debris and so on, right? So there are lots of technologies that are being built in this space now, and I'm just going to introduce you to some of these things, and then I'll close my talk with some open research pointers that might exist, and you may ask some questions. We may interact on certain things that if you find something interesting that you want to pursue, we can do a little bit brainstorming towards the end. So there are two key pain points in such scenarios in emergency responses. The first one, as I told, was unable to communicate. So destruction of communication infrastructure, and then cellular networks, often the sole communication medium, they become non-operational or they are destroyed, right? So you cannot communicate, so you don't know, you cannot talk to the colleagues or the people who are in the forefront, right? You cannot discuss among people and then make a coordinated access to the region with in a much more planned way. And the other one is the unable to track thing. So disaster site often indoors or under debris or heavy foliage, they lack access to GPS signals. So they're not able to trace the victims' locations, or sometimes they are not even able to trace their own colleagues or even themselves. right? So it is very difficult for them to prioritize the efforts in a certain area. So I need to send more troops to an area where you need them more, right? Where there are more victims, I need to spend my resources there. Right? But since we don't have these resources, we have to do something like blindfolded, right? We just test our luck and go to every corner and try to look for victims, right? So we can try to see how a combination of sensing as well as communication can help address this problem to some extent. So, as I said, drones can be useful. They are wireless communication capabilities. They can be equipped with wireless communication capabilities. For example, you can put an access point on top of the drone, and you can send the drone to a desired location, and they will be beaming some Wi-Fi network to the region underneath. Right? They are rapidly deployable. You don't have to have a permanent infrastructure, so it's on demand. It's lightweight, right? It's not, it doesn't require a huge truck to carry the drone. It could be a small one, and it's low cost. You don't have to have a cost of uh, tantamount to having a big truck deployed with a cell tower, right? It's not, it's much more lightweight and cost effective compared to that. You can very easily carry them to rural areas, and there's a lot of research advancement nowadays. Why this becomes more and more popular now is a lot of research advancement in this end is happening, both in robotic side, control engineering, IoT. All sorts of people are working on these aerial platforms, and this is the right time to explore these options for flying access points or flying, let's say, LTE base stations, right? And they are already being used for surveillance. It's not that the police or the public safety entities are not using them. They are already being used, but more of an extent of using the camera or taking a video feed and so on. But we want to piggyback the system also with communication and sensing capabilities. But the problem is that it's if you want to give uniform access all over the place, it will be over provisioned, right? You have to actually put too many of them where we are not sure where the victims are to give them an uniform coverage. So in that sense, we have to do a blindfolded way, proceed in a blindfolded way, and make a statically deployed uniform coverage, which will not be economically viable, or it will have a huge control overhead, because all these drones will be controlled from a base station, or even if it is automated, the law requires you to have some personnel who is going to watch on the drone, right? And clearly, if you have lots of drones, it is not possible to do. And if you just have one, as you see in the bottom side, like the bottom picture, it will lack the essential coverage, right? Since you are not sure where you have to put the victims, where you have to put the drone in order to help the victims, you will have lack of essential coverage. So you cannot send the drone to the essential locations where you need them the most. So this is sort of an introduction to how drones can be a new useful thing, right, in this space, right? And so today I'll divide the talk into two parts. One is based on the connectivity side. How can you enhance connectivity in this scenario using drones, and what are the research problems that exist in that domain? And the other one is on the sensing side of such systems. And there we will see that since we have already seen that we don't have access to GPS, and also any other infrastructure that might have existed is destroyed, how the drone itself can bring infrastructure to perform sensing, and in order to retrieve the locations of the victims. So the victims are trapped inside the building, or the victims are trapped under debris. We somehow want to figure out the location of those victims. That is one application. And the other thing is also when the first responders or the people who are actually doing the search and rescue operations, they can also enter the building, right? And they also need to be tracked, because if somebody needs medical attention, you have to immediately send the medical group to rescue him and take him to a hospital, right? So it's very important for the firefighters or the rescue mission people. They need to be tracked, right? So we are trying to use this drone for both the purposes. So these are the two papers primarily I was at NEC, and some of this extension of the work that I'm currently working on. So I will primarily cover these two papers. So somebody who is interested in order to look more into this, you can go to my website and check out these two papers which were recently published in 2018 and 19. So first I'll start with the SkyRAN paper which was published in Phonext 2018, followed by the sensing work that was published in Usenix NSDI in 2019. Okay, so if you have any questions, if you have doubts, please stop me and ask. And anyway, we will discuss some of these things towards the end of the talk. Okay, so think about situations like this. This is a picture from Hurricane Fani that happened mostly in Odisha, Andhra, and parts of Bengal, right? And there's a huge scale of destruction, and not a single communication entities were alive, right? Most of the base stations were taken down. And how can we bring this drone in order to solve this problem? That is the focus of this talk. And that's why I named it When Mobile Networks Fly. Can we have a flying base station who is going to give the coverage on demand? So the UAVs are kind of carriers of on-demand wireless network infrastructure. So this is the first part that I will focus on. How do you get an efficient communication across different devices that are deployed on the ground? And the next part is, how do you also impart localization to them? How do you know where the victims are located, or how do you know where the first responders are located, so that you can give a better quality of service? You can manage the troops in a better way, in a more economic way. Okay, so I'll go to the first part of the talk, that is SkyRAN. So this is the scenario. So you have this entire area where this destruction or some natural calamity has taken place, and I have shown the UVs, or the user equipments, or the cell phones, as those small rectangular boxes on the ground. So some smartphone icons I have shown. And apart from that, you also have this control station, which is a truck which is kind of not at the exact location where the destruction or these calamities have taken place, but maybe it could be at a little bit farther away, right? And the actual locations might not be accessible by these trucks because of landslides and so on, right? And that control station has access to a macro eNode in case of an LTE station, which gives you access to the internet, right? But it's not mandatory. If you don't need access to the internet, you can be a self-contained local network. That is also possible. Okay, so our vision for this kind of a system is on-demand, highly flexible, low-altitude UAV communications when fixed infrastructure is not available or destroyed, right? So we name the system Skylight. Like from the sky, we are as if beaming the LTE beams. So this is the way we are going to deploy. We are going to put a few drones on that area, and the drone will have control access from the control station. Some of the control messages, or the trajectory of the drone, how it is going to fly, where it is going to station at, will be controlled from the control station. And at that particular location, it will be beaming the LTE signals to the ground, right? So next, as you know, apart from having this control signal, it will also have data connectivity. So either it could be connected to the satellite. Some of the bigger ones, the expensive drones, you can have a radio that is able to do a data access to the satellite in order to give you internet access, or you can have a data connection in a wireless link from the control station also, right? And the control station, as you have seen, could be connected to a macro eNode V in order to give you data connectivity. Okay. Okay, so now this basically shows you the infrastructure of the setup, how the drone-based system is going to be deployed in that area. And the Skylight system consists of three parts. As you understand, there is a RAN part, or the radio access network, with the lower one. So that takes care of the connectivity of the UE clients of the mobile phones on the ground to the drone, right? So that is basically the radio access part of the front haul part of the network. Then there is a core network. Because this is an LTE connection, you need the EPC core and things like that for managing the all the accountability in the network and making the connections, all the LT specific protocols. And then you also have this layer called sky haul, which is basically the backhaul, which is connecting multiple drones together. Suppose you want to send data from one mobile phone. Let's say on the left hand side I show the police car, and on the right hand side I show the fire truck. So suppose you want to exchange data in between these two cells. So first what happens, you need to send the data to your local drone, and the local drone has to send the data to the other drone, and then the drone sends the data back to its own cell, right? So you need to manage this backhaul network among the drones, right? So there are some connectivity issues that has to be looked at when you have to look at this specific backhaul network. How you want to place the drones. If there are multiple drones, right, you don't want them to collide among each other, right? And at the same time, you need to have the backhaul network accessible to most of the clients, right? So there are different research problems here, and this is not specific to LT, right? If you just remove the Sky core part, it can also, all the algorithms that we are developing is generic, right? It can apply to any sort of wireless network. For example, we can even have Wi-Fi, right? Instead of having LTE and getting rid of those EPC cores and so on, you can simply put an access point, wireless access point on top of the drone. We still have the Sky RAN part as well as the Sky Hall problems to solve, right? So whatever I will kind of discuss today, the Sky RAN is sort of generic to any wireless network that you want to put on the on the drone, right? So in that way, it will be sort of the algorithms that we develop would be kind of useful in many sort of use cases in different kinds of wireless network, be it 3G, Wi-Fi, or some other kind of proprietary wireless network. These principles doesn't change. Okay. So what is the main problem in this Sky RAN, right? Let us try to understand that, right? So you have multiple UVs or mobile clients on the ground, and your task is to give them optimal connectivity from the drone, right? That's your task. Okay. So what I mean by good connectivity, there are two things. You need to give them good coverage so that most of the clients are covered. You cannot leave out some of the clients, right? It might happen, but you want to try best so that nobody is left out. And the other thing is that you also need to give them good capacity, which means that the aggregate bandwidth of this entire system should be as high as possible. You need to maximize the aggregate throughput of the capacity of this network. Okay, so these are the two things we want to look out for. We want to give good coverage from the drone. So I have to put the drone in such a position in air such that most of the clients or maximum number of clients are covered, and at the same time the aggregate capacity or the total throughput, aggregate throughput for all these mobile devices is maximized. Okay, so now it becomes like a search problem. So this is a 3D space in air, and we want to go to one naive solution is that you want to go to some location and test out that whether your coverage is good or the capacity is good enough, right? So whatever we call connectivity. So we can do some hit and trial. So suppose you are here, right? So as you can see very clearly that the coverage is not good. Some of the mobile phones on the right hand side are left out because of the position of the drone. And so this is good capacity, but not good coverage. So this is overall the connectivity is not something that is desirable. So this particular position of the drone is not a good candidate in your search space, right? You want to go to such a location which optimizes all of them, at least to some extent, right? To some maximum extent possible. So you plan to go to a different location. So the drone now comes to a different location. Now you have good coverage, right? Because all of the mobile phones are now covered, but you have moved up, right? So your signal strength on the ground decreases. So some of the nodes might have moderate capacity, and as you see, some of the mobile phones on the right hand side has poor capacity because of shadowing, right? Because of the presence of these obstacles or these trees in this example, they will lack access. good access to the wireless signals. So maybe this can be made better, right? So this might not be a very good or the optimal candidate for your search space in this case. Okay, so we plan to go to another location, let's say. And here also you have the same problem. Although on the right hand side, these mobiles regained connectivity or good capacity, whereas on the left hand side, the UEs do not have good capacity. So this also might not be a good candidate for placing your drone. And similarly, you can go to a lot of these different places, which is equivalent to a brute force search. And finally, you can come to some obscure location where you can satisfy both the conditions. You might have good connectivity and you might have a good capacity, which is sort of an optimal position for the UAV or the drone. Right. So I try to use these terms interchangeably, drone and unmanned aerial vehicles. Yeah, but yeah, they sort of mean the same thing with different connotations. In this talk, I'll try to use both the terms. Uh, so so in this search space, we sort of got one location where this satisfies both the conditions, coverage and capacity. And it might not be that there is only a single location which serves this purpose. There could be multiple ones, right? And now in this figure, what I show is on the top, you will see an average throughput, right? Which is basically capacity. And this is a CDF, which shows the variation of the throughput. Given that you can place the drone in so many locations, I basically plot the empirical CDF, or you can even think of in terms of a probability density function, where I can show the distribution of the throughput at different locations. And on the bottom side, I also show the heat map, where if I place a drone in a certain 2D area, what is the capacity that I am getting from the number of phones that I have deployed on the ground. Suppose I have 10 phones, and out of those 10 phones, how much total throughput that I can get or I can achieve from the system. So this is an experimental result where I show at different locations, I have different throughputs. As you see on the bottom side, I show poor throughput, which is close to 3.7 Mbps, whereas I can go, the optimal throughput can be as high as 30.3 Mbps, right? So even if you go to a moderate location, that gives you something around 27, 26 Mbps speed, which is close to 30.3. However, there are pockets where you can get really poor throughput, right? So if you randomly put somewhere, right, the drone in the 2D space or in this 3D space, because the altitude also comes to play, as you will soon see, you will get something like, as I have shown in the figure, something like 18 Mbps, your median in the CDF, right? Which is almost 10 Mbps lesser than what you can possibly get, right? Let's say your good throughput is 27.6. This is almost 10 Mbps less, right? So randomly putting the UAV is not an optimal, it's far from optimal, right? If it was not, if it was very close to optimal, we should not have thought much about it. It might not have been an important problem to solve. But as you see, you don't want to waste the battery of the drone flying the drone and putting that in a suboptimal position where you can get so poor throughput, right? This sort of motivates why we try to want to scientifically look at this problem. Okay. So now, as you have understood, this has become like a 3D search space. So there are two factors here. So the first factor is, where do you want to place the drone in the 3D space, right? So this is one thing. And the other thing is there could be so many locations of the UVs on ground, right? So however we are solving the problem is basically, given the location of the UVs on ground, we are coming up with an optimal solution for placing the drone. However, there could be many possible locations where the drone could be, where the UVs could be at, right? In all this entire 2D area on the ground, there could be UVs, right? And we are not sure where they are. So the complexity of the search becomes on the space where to put the drone, that is like n cubed in terms of this unit boxes that I have drawn. And on the ground also, if you imagine in the 2D plane, we have this boxes around, there are like n square boxes, right? So the complexity of the search is very high, and we cannot use a bootstrapped way or brute force way in order to look for the optimal location for operating the drone, right? So this is sort of needle in a haystack problem, and this is the main systems engineering problem is how do you systematically search for the optimal operating point. And there are constraints like the UAV has limited battery power; it won't fly more than 30 minutes or more than not more than an hour, even with this more sophisticated drones with lot of batteries. It doesn't go more than that in most of the cases. And we don't want to waste our time searching for the optimal location, right? Rather, we want to go and park at that location and give the connectivity to the clients. We want to give networking support to the clients rather than wandering around and looking for an optimal position. So we want to finish searching for the optimal operating point as soon as possible under these constraints. And these are the reasons we make this problem sort of interesting to look at. Okay, so these constraints are real constraints, and it's an important problem as we have seen. And the motivation was kind of laid by the statistical analysis that we have done by actually deploying the drone in so many locations. Okay, and so I will discuss now our approach, how Skyran is trying to solve this problem. So what we were trying to do here is estimate the radio environment map. So this is the signal strength map, you can call it, and the distribution of the signal strength over the spatial the plane or the 2D plane, right? So that is the first thing we want to do. So for every UV on the ground, we will have a radio environment map, right? So what is the value of the signal strength at a certain 2D point, given that your UV is on the ground? So that map is done and it is known as the REM for a certain UV. And you do it for all the UVs, right? I will explain how to do it because this data is not free. You cannot get this data. It's kind of, you have to do some measurement and sampling, and that is going to add to your, waste your battery life, right? I'm going to tell you what kind of heuristics could be used to obtain this. So first is this stage, right? We want to know what is the radio environment map or the signal strength map for these different UVs. The green could be very high signal, and as you move out from the UV, the signal strength become poorer and poorer. Okay, and then we want to compute the aggregate REM for all the UVs. So it could be a median function or it could be a max function, 95 percentile function somehow, because we want to give preference to all the UVs, we can somehow merge them and try to see where is the higher signal strength, right? Because all these individual radio maps will have higher signal strengths at different locations, and we want to find out those locations which are more important in a statistical sense, right? So that f dot is the utility function of your choice. It could be median, it could be max, whatever you choose. And then, as you understand, we have to find out the location that maximizes the utility function. That we want to go to the place where the signal strength is the expected value of the utility function rather is highest, right? And we want to go and place the drone there. Okay. So now, as you see, these are the 3 steps, out of which the first step basically entails a lot of calculation, because you have to get the radio environment map to start with. There is nothing like that to start with, and you don't even know where the UVs are located and so on. Okay, so the first thing in order to, before even estimating the radio map, is to find out the altitude, right? First, I need to know at what height to operate at. Then only I will know where to operate at in the 2D plane. So for doing that, at a certain point, we basically climb in the z-axis, and we basically try to see where my signal strength is maximized, right? So if you actually look at the RSS plot of in this particular scenario, it looks something like this. So once you are on the ground, because of the foliage and on the obstacles near the ground, you will have a very high path loss or a lower signal strength. And as you climb up, your signal strength gets better and better because some of the obstructions are now cleared off, and from a certain location on the air, here in this case, I was like close to 40 meters, so it can go high up in the air, this kind of a drone. And from that particular point in air, I could get a very clear view of the all the UEs, and there we had an optimal value of path loss, which is something like 75 to 80 dB. And then once we go up from that point, the signal kind of fades away continuously, right, as we climb up more and more, right? So in this way, we can find out what is the optimal altitude for us to operate. So that sort of gives us a clear idea that which 2D plane we should be able to explore now. Okay, so track the LTE path loss while the UAV climbs up vertically. The path loss shows a local minima at a given altitude, and we should basically go and grab that particular local minima, right? And most of the cases, right, if your uh, terrain is not very complicated, it will also be a global minima. Right? In some cases, you might actually be trapped in a local minima. So in that case, you can shift to a different location and climb up, right? So all we care about in this stage is getting hold of the right value of altitude. And then also note that we don't have any idea about where these victims are located, right? Or the phones. The phones are basically carried by the victims on the ground. So we have to first localize those phones itself. So what we do is, in case of Wi-Fi also it is possible, or even LTE, from the SRS symbols, right? The time of flight can be calculated. So for people who are not aware of the internal details, you can just assume that the time of flight is the time taken by a signal, a wireless signal, from the drone to the UV. What is the time that is taken by the signal, right? And that multiplied by speed of light, because all the signals travel at the speed of light, it will give you the distance from the drone to the UV, right? So the wireless technology is going to offer you some modality by which you can calculate the time of flight. It could be ultra wideband, or it could be, as we'll see later, or in case of if you want to do it using the existing communication system, let's say Wi-Fi or LTE, there are ways in order to calculate this time of flight. So once you calculate this time of flight, what we will do is we will calculate this time of flight from multiple vantage points. So TOF1 multiplied by C is distance 1. Then we have distance 2, we have distance 3 till distance n. And what is the unknown thing here? X and Y is unknown. We don't know the location of the mobile phone on the ground. But what we know here is the location of the UVs. Okay. Location of the drone, because the drone has access to GPS. The drone is flying on the air. So we know the location of the drone and the time of flight to the UVs. So using that, we can use a multilateration, which basically can help you to solve for X and Y. So in the next part of the talk, I'll go into more details about how this is calculated. You will have a better idea. For now, you can assume that we have a crude way of estimating the location of the UVs on the ground. And that, of course, comes with some errors depending on the technology used. So in this case, we can get the median localization accuracy of about 5 to 7 meters. So X and Y, whatever be its location, we are getting an X prime, Y prime. We are estimating the location as X prime, Y prime, which is like 5 to 7 meters from the true location, right? That is the error that we are introducing in localization. Okay, so now we have done the first thing. We have climbed to the right altitude. The next thing is we have sort of localized all the UVs on ground in this way. And now the third thing is that we want to look for the optimal operating point. Okay, so how do you start? We start in this way, that we have to estimate the REM, or the radio environment map, and we know the location of all the UVs with a certain error. 5 to 7 meters error is there, but we approximately know the location. So there are generic path loss models which basically says that with distance your signal strength is going to fade away. At the location of the transmitter it is highest, but with distance it is going to fade away. What we don't know is the knowledge about the terrain, right? If there is a certain building on one side, of course, the signal strength is to die down further compared to if you don't have a building, right? So we don't have any information about that to start with, right? But since if you know the location of the UVs at least, you can simply assume a simple path loss model and initiate the REM, right? So in this case, the REM could look something like this. So you have these two mobile phones, and for these two mobile phones, we know the REM on that particular uh, altitude in the 2D plane, something which is very regularly shaped. So very high at the center, and it dies down as we increase the radius of transmission, right? So this is with zero information from the drone, right? It's just now we have uh, just have a simple path loss model. Now what we will do is we will uh, use the gradients of the superimposed REM. Now you have this two REMs. In a practical case, you might have 10 REMs together. You superimpose them, and after you have superimposed, you will see that there are some location where the gradient of the signal strength is very high in the combined REM. So there you will basically have much more information. So if you make the drone travel through those gradients, that raw data will be able to add much more information to your combined REM. Okay, so that's why I have written that signal gradients implicitly encode more information about the terrains. So suddenly the uh, signal strength was high and suddenly it has become very low, right? Which means there is a high gradient, and that also means that there could be obstacles present. There could be a building present, or there could be trees present, and so on. But for that reason, the signal strength has suddenly dropped, right? The gradient is very high. So if we go and collect more data in those locations, it will be more worthwhile given the amount of time that I want to fly. Okay, so I'll follow a straight line path through these points that are connecting the gradients, and for doing that, I am basically minimizing the trajectory, total trajectory, by using the traveling salesman problem algorithm, right? So there are not a lot of points that we want to cover here. It just basically depends on how many locations we have this signal gradients at, and we are basically joining those locations using the minimum path, right? So even if you do a brute force approach, it is not going to take that long, right? It's not 50 or 60 cities that you want to connect. It's just 3 or 4 small clusters that you are connecting. Okay, so and by doing this flight, you have expended some of your budget, right? Suppose you want to fly for 20 minutes, you have already flown for, let's say, 5 minutes here. Okay, and next you want to update the signal, the REM, because you have now flown, you have access to the raw data. So whatever simple path loss model you had, you now add some more raw information to that, and it becomes much more enriched now. Okay, and you have budget left. Let's say you have only flown for 5 minutes, you can fly for 15 more minutes out of, let's say, you have a budget of 20 minutes. Now you can do one more iteration of the same thing, and that will add much more information to your radio environment map, and you can repeat like this before your budget is exhausted. So whatever time you wanted to plan for your search time, let's say it could be 5 minutes, it could be 2 minutes, 3 minutes, depending on your application. Your budget is exhausted, and so this is the kind of the closest approximation of the radio environment map that you have now. Okay, so you did not have any knowledge about the terrain, you did not have any knowledge about the location of the UEs, but you have done all of it in this finite amount of time. Okay, and we were trying to minimize your flight time and maximize the information that you are collecting about the REM. So this is sort of a heuristic that proved to be very useful for us. And just to summarize what we do, we operate this in epoch. So in the first time, in the first phase, we do a localization. How do you do the localization? The drone has access to GPS, as well as it calculates the time of flight information from LTE or Wi-Fi, whatever be the technology. And then it does a multilateration to compute the location of the clients. That is part one. Now, once you know the location of the clients, you have to calculate the REM. Okay. So for doing that, we do three things. First is we go to an optimal altitude. We know at what is the height I should operate at. Then I plan for the trajectory because I want to enrich my REM. and keep on updating the REM, right, as I fly. Okay, so in that way, after I am exhausted, I have exhausted my budget, I have this aggregate REM ready, and within that aggregate REM, I can find out the optimal position simply by knowing at which location my utility function is high. Okay, and then we can just move to that particular location and give an LTE service, right? So there is no problem with this particular thing. And what we might face is there will be dynamics that will be associated with the clients. The clients will move their position, right? Let's say this is a disaster situation, or there is a big fire that has broken out. People will go here and there, and based on that, the location of the victims will continuously update, right? And so we'll keep on monitoring the performance of the UVs, because we are serving as an access point, or we are serving as a base station. We can have a good knowledge about the performance of these different UVs. Instead of actively tracking them, we can just simply know that what is the average throughput that we are getting. And once we see that there is a substantial drop in throughput, we can do this epoch one more time, right? If the performance of the UVs is poor, we can go back and repeat the process of doing the localization one more time and updating the REMs, right? And by the way, we can use the historical information for UVs who have not changed their location. So some UVs will change their location, and some UVs will not change their location. So we can use that historical information. Okay, and this is a real implementation. So some of it was done as I was at NEC. So we actually put the LTE base station with the eNode B and EPC on top of the drone. And on the right hand side, this is the ground truth data collection, where we actually covered all possible points to know what is the optimal operating point. Right? This is for actually cross verifying our algorithm or our heuristics with the ground truth. Okay, so this is a huge amount of data collection that has happened. And if you can see, there is a screenshot I have shared. This mobile phone is actually connecting to the drone. It's not connecting to some other commercial network provider. It is actually connecting to our drone using the, we were using this open source thing called OAI EPC. Open air interface, it is called. You can look it up if you have interest in this domain, or you want to research a little bit more on this. So these are all open source tools that help you to construct an LTE network of your own, and even have a phone connect to it. You can do a phone call using your own LTE network that is set up. It's just that what frequency you use, it's a little bit dicey question. You have to do it inside a lab, right? Otherwise it becomes like sort of a legal issue. Okay, and these are the performance metrics. So as I told, on the bottom we have the x-axis, we have the measurement budget. So instead of time, we are doing it in terms of meters, how many meters we fly. And if we just do an uniform trajectory, as in this problem, as in on the ground truth, right, we are just doing an uniform trajectory, just moving left and right. So it will take a long time for us to know the optimal operating point, right? And on the x-axis, I have shown that what is the relative throughput with respect to optimal one. So if you get the optimal throughput, that is 1. So what percentage of the optimal throughput I am able to achieve? So if you see, if we have a budget of 1000 meters, we are almost getting close to 90% of the optimal budget, right? Whereas if you randomly put your drone somewhere in the 2D space, it will get much more lower than that. Just an uniform trajectory, as you see, it is always getting something close to 40 to 50% of our Skyran, right? So this shows that this kind of heuristic helps, right? And some random solution is not going to help in this particular scenario. Okay, and slowly there is also this problem of diminishing returns. So initially your benefit is very high, but as you increase the budget from 600 to 800, from 800 to 1000, there is not much improvement. Okay, and the other thing is that even for large areas, it can very quickly go to the optimal. It can go to 90% of optimal throughput at a very little time, right? Whereas the uniform trajectory might take a huge amount of time. So in case of terrain like New York City, where there are lots of buildings and so on, the trajectory or the terrain is very complex. In that case also, in a certain area, of course, not the entire city, is a certain about 300 meter by 300 meter area, we could do a search within less than a 5-minute time. Okay, so there are more details in the paper that you can try to look at. Okay, so there are three takeaway points. So this was the first of its kind system where the entire LTE stack was hosted on the drone. The drone was not tethered with any optical fiber or any other electrical cable or anything to the ground. It was completely released and free to move. And for the Skyran, it was adapting to the changes in the overall UV location to maintain its connectivity. So even if the UV changes their location, it will automatically trigger the drone to update its location, and it can achieve 90 to 95% of the optimal throughput with moderate flight time budgets. So we don't have to fly the drone for a huge amount of time. Within a decent amount of time, we can get 90 to 95% of the optimal throughput. Of course, there are downsides to it. Depends on the terrain complexity. We did try out 3 or 4 types of terrains, and some of these are real experiments. These are not all of them are simulations. So whatever pictures you have seen or the data has come from actual experiments of flying the drone. But we could fly the real drone in limited locations because of permission issues. More experiments could be done in order to understand the real flight time and so on, right? And there are theoretical works which also look into this particular problem using simulations and all, but they again lack the real flavor of determining the signal strength distribution, right? Most of these works are based on estimating the signal strength distribution of the REM. But yeah, this in simulation will have much more, will be much more less realistic compared to what you can get in an experiment. Okay. And with this, I will go to the next part of the talk, which is more on the sensing side. Now we have covered the communication part. We have provided on-demand connectivity. Now we want to do an on-demand localization, right? And why do you need on-demand localization in these cases? Because in these GPS denied environments, wherever there are these disasters, they don't have, most of the cases don't have access to GPS. There are these IMU sensors in your mobile phones. They have this collection of accelerometer, gyroscope, and compass or magnetometers that will drift drastically with time unless and until it is corrected, right? And there is no correction or fix that exists, right? If you just have your mobile phone and simply walk with that and try to track your location using the IMUs, it won't work for more than few seconds, right? Whereas these operations might take tens of minutes or like maybe close to an hour, or sometimes it can take more than an hour, right? And there are no access to indoor positioning infrastructure. You might have these beacons that we see in a lot of literature. People are talking about this Bluetooth beacons or Wi-Fi beacons, deploying them. But in this case, everything is destroyed, right? There is nothing we can rely on, right? Or if there is a terrorist attack, there could be things that are not secure, right? Things could be compromised, or that will give you a wrong value or so on, right? Just to confuse you. So, and another thing is that the tracking needs to be real time. So if you are sending troops inside the building from outside, we should be able to track them, right? In order to save their lives or make sure that they are not in danger. Okay. So these are sort of the motivating factors. Why do you need a GPS free solution indoors? And we are trying to see that how can we bring this kind of a solution in our drone based system, which are already being used for communication. Okay. So a little bit of tutorial about this thing that I was talking about earlier. So how does a wireless positioning system work? So let's say you have a wireless device that is denoted by this black dot, and we need one location of a probing device. Let's say a probing device could be located at a point x1, y1. And what we do is we try to calculate the range in between the probing device and the wireless device. And the range could be calculated, as I told you earlier, from the time of flight information, TOF. So the time of flight multiplied by speed of light will give you the range, right? You know the time, you know the speed, so you know the distance. So for any wireless localization to work, ranging is fundamental. You need to calculate what is the range in between these two wireless devices. And once you have done this, what is the locus of the wireless device? The wireless device could be located anywhere in this circle, because you have you know that your location is x1, y1, and you have probed the wireless device, but it could be anywhere in this radius, right, on the circumference of this circle, because the range is fixed. So to correct that, you have to use at least 3 probing locations. So this is the second one, which will give you 2 points, one on the top, the intersecting point of these two circles, and one on the lower side where they are also intersecting. Now to remove this ambiguity, you need a third location. So only if you have these 3 locations for the probing devices and 3 ranges, range 1, range 2, and range 3, then only you can solve the simultaneous equation in order to solve for the location of the wireless device. The 3 ranges, R1, R2, and R3, and 3 locations, X1, Y1, X2, Y2, and X3, Y3. These are all known. So you can find out the unknown location XY of the wireless device by solving these 3 equations. Right? You have these 3 quadratic equations, and you have 2 unknowns X and Y, and solve them. And it is a 2D case. If it is a 3D case, you have X, Y, and Z. In that case, you will need 4 equations like this. Clear? Okay. So as I told you, now we'll talk about how precisely you can track these devices. So this is a fundamental equation, range equal to time of flight into speed of light. So how do you find out the time of flight or the resolution of the range? So there is a transmitted pulse that whenever you are sending the signal from the transmitter, and there is a received pulse, right? The pulse will be received by the receiver. So how accurate your time of flight will be calculated will depend on the resolution of the time that wherever you are receiving the signal. Right? The more closely spaced time resolution you have, better is the granularity of your time of flight calculation. Right? So if your resolution, you have to achieve a better resolution, what you need is basically a better bandwidth of the signal. Right? People who have worked in some of this taught in this classes, where in signals and systems, or if you have worked on FFTs and so on, you probably know of this kind of, you will have this background, right? So better you only want to do in terms of time resolution, you need a better bandwidth, right? So the range resolution is basically 1 by bandwidth into speed of light. So if you actually use technology called ultra wideband UWB that has close to a gigahertz width of bandwidth, you can do as good at tens of centimeters. So your range resolution can become erroneous to an extent of 10 centimeters, not more than, not meters. Whereas if you are using megahertz, right? In case of Wi-Fi can go up to 80 megahertz or 160 megahertz, right? In those cases, you might have meters, right? They cannot fundamentally allow you to go to centimeters. Okay. So bandwidth, as you are seeing, what technology you are using for probing the device, as and this example here. So what is the wireless technology in between the probing device and the wireless device? What is the error in the range? That depends on the bandwidth of your technology, whether it is Wi-Fi, whether it is LTE, because LTE is even less, right? It can give you 20 megahertz of bandwidth, right, in the frequency spectrum. Whereas the ultra wideband can give you something like 500 megahertz or 1 gigahertz. So that can be used if you want to get a very good ranging precision or good ranging accuracy. And at the same time, that will also give you some kind of penetrability, because if these are indoors, right, you have to penetrate, the wireless signal needs to penetrate from outside to the indoor location, right? So that advantage or that kind of capability should be there in the wireless modality of your choice. So now this multilateration performance, the solution for X and Y, it will depend on several things. So this is our scenario. The wireless device is located indoors. XY is the wireless device. It could be a first responder who is trying to look for victims, or it could be a victim who is having some kind of a wireless device. So the first is the precision of the estimated range. So ultra wideband technology is offering you 10 centimeters accuracy. So if they are connected using UWB, the range that we will calculate will be pretty accurate. And the other thing is we need a flexible vantage points in the 3D aerial space. So these are the probing locations. The red points are probing locations that we have shown using X1, Y1, X2, Y2, and X3, Y3 in the previous example. So here, if we use drones, they are an attractive way to cover the spatial vantage points. Right, in the 3D space, we can move the drone across these points, and that can give you a good enough number of probing locations. So the drone can actually move outside the building, and we are already using these drones, let's say, for giving communication bandwidth. So there is no other problem. The drone anyway moves here and there. So this drone can also give you this probing locations for ranging the wireless device. Okay, and the drone will have access to GPS. It's flying up in the air, so it has access to GPS. So the location coordinates of the probing spaces are known. Okay. So what is the solution? I'll discuss the solution to some extent. So as you understand, the drone goes through a series of locations, and after going through the series of locations, it will find out the location of the people inside. So we show a building map, and within the building map, let's say there are these 4 first responders who are looking for victims, whether anybody is trapped inside this building, which is on fire, let's say. Okay. And the UAV or the drone collects as many ranges over time. So range is the distance, as you know, from the drone to the first responder, and it collects as many of them as possible over time. And the trajectory forms what is known as a synthetic aperture. So the collection of this x1, y1, x2, y2, x3, y3, this collection of these points is known as the aperture of your system. And this is synthetic because we have artificially generated it over time, right? It's not that the drone is standing. There are like multiple drones. There is only a single drone which is covering all these locations over time. So we call it a synthetic. It has been synthesized. The aperture has been synthesized temporarily, right? So the drone moves through all these probing locations, giving rise to this synthetic aperture. Okay, and you have location coordinates of the drone, so it can help you solve the location of the person. It works fine for static nodes, no problem. So given the system, it will work perfectly well if the person inside the building is not moving, he is static. But this is not a practical situation, right? It doesn't happen in reality. A first responder who is entering a building will run around and he will change his direction. All sorts of things will happen. Okay, so for making a robust engineering solution, we need to do something more than this. Okay, so suppose the person is actually moving over time. So the ranges that has been collected in the first part was corresponding to the initial location of the person, whereas he has changed his location, as I showed in the shades. Towards the end, the drone is collecting the range that is corresponding to the latest location of the person, which is much ahead than where he was in the beginning. Okay, so a mobile node in this way, we cannot solve for the location of the mobile node like this, right? Because all the values of x's that we are solving for is changing over time. So you will get an erroneous solution. The next problem is that another challenge is people can take turns, right? He might not always move in a straight line. He can even take turns, and we sort of have to come up with a solution for knowing that the person has turned, right? And we have to again reset the solution or try to adapt the moving person's trajectory in our system. Other problem could be, as you see, any wireless technology will only have a limited reach. It cannot go hundreds of meters inside a building, right? There are walls and there are furniture. So we have to do something about this also, that how can you augment or how can you improve the system so that we can also cater to limited reachability problem. Okay, so let's see how our solution tackles most of these problems, or like all of these problems to a certain extent. So we'll talk about the mobile node problem. So how we are solving the equation for this unknown location. So at a certain point of time, let's say at time ti, the location of the first responders is xi, yi, and zi. Okay, and the drone's location is cxi, cyi, and czi. What is the value of the range ri? Ri is the distance that was measured at time ti by the drone to the first responder. So ri is the range, and I have just written the Euclidean distance in between the drone's location and the first responder's location. So RI is an estimate of the Euclidean distance in between these two things. So RI is known in your system because you have measured RI. CXI, CYI, and CZI are known because it is actually obtained from the GPS locations. XI, YI, and ZI are not known. You want to solve them. Okay. So these are the drone locations, as I told you. These are the node locations or the first responders locations. Okay. And now, if I simply use kinematic equations, what is the value of xi? Xi is equal to xi minus 1 plus Vx is the velocity in the x direction. So suppose you have like two orthogonal directions, x and y. So Vx is the velocity in x direction multiplied by delta Ti. So there is some time gap that you have in between two range collections. Let's say 1 second, 500 milliseconds, whatever be the time. Velocity multiplied by that will give you the displacement in the x direction. Same for y direction. And if you do it sort of recursively for all these locations xi, yi, and zi here, so suppose he has started, he is running from x1, y1, and towards the end where I want to do the multilateration, he has reached x5, y5. Okay. So x1 is nothing but Vx multiplied by sigma I is equal to 1 to I if you have 5 entries, 10 entries into delta Tj. So those are the time gaps. Okay, so this is a simple kinematic equation where I am just adding velocity into time and I am having an innovative use of that. Okay, that is what is important here. Okay, so all I have to now measure or estimate is instead of having two unknowns x and y earlier, now we are solving for x1, y1 and Vx and Vy. So what was the starting point of that person while he started running, right? Because for all locations, he will continuously change his position. And what was his velocity in the x direction and what was his velocity in the y direction? So if you solve for these four variables, you can get a good answer to all of his trajectory. Right? Once you know Vx, Vy, and you know the starting location x1, y1, you can solve for the rest. Right? Okay. So this is the optimization problem. So we want to minimize this function. So Ri basically is the range that you have estimated, and this is the Euclidean, the square of the Euclidean distance. And we are basically trying to do this least square error, right? And getting a value of x, y, vx, and vy. So this solves for the node mobility by not solving for the location, but for solving for the velocity. Okay. So just having the naive multilateration, as you see, can introduce a lot of error, right? Suppose the person is running at 2 meters per second, you can get an error of 10 meters, right? So inside a building, if you have 10-meter error, it is almost like there is no use to it, right? 30 feet error doesn't make much sense. Whereas if you are using solving for the velocity vector, that gives you a much better accuracy, localization accuracy, and you can see we can bound the error almost by 2 meters or 3 meters at the most, right? We are getting something like 30 to 40%, or actually 300% improvement, the 3x or 3.3x compared to your naive multilateration technique. Okay, so just see a minor modification of multilateration, how it can give you huge improvements, right? Instead of solving for locations, we try to solve for velocity, and then simply solve the nonlinear least square kind of a problem. Okay. Now, how do you tackle turns? Another simple thing, but it's difficult, right? From the drone, you just have access to range equation, the ranges, nothing else you have. How do you tackle the turns? How do you know the person has changed? Till now, the velocity thing that we were showing you was assuming that Vx and Vy are constant. He's not changing his direction, right? Then your Vx and Vy value will change. So we have done a nice trick here that I'll share with you guys. So if your aperture, the size of the aperture is small, your historical data is less, right? On the left-hand side I've shown. So if your aperture is small, your localization accuracy will be also poor, right? The span of x1, y1 to xn, yn is very small. So the amount of variation that you have seen in the range is small, which basically gives you a poor accuracy in localization. However, it adapts to the velocity changes, because the next time the person has changed his location, but you have changed your aperture also. So if your aperture is small enough, your time that you are giving for the person to run is also small. So there is a very less chance that he will change his direction, let's say within 1 second or 2 seconds. Whereas if your aperture is very large, there is a high chance that within that large amount of time, he is bound to change his direction here and there. So it will adapt very slowly to the velocity changes. However, if the person was static, your localization accuracy will be very good, very good. You will have a lot of vantage points to sample the data from. Okay. So keep this intuition in mind, and we want to do the best of these both worlds, right? Whether we want to use a smaller aperture or we want to use a larger aperture. Okay. So you see, in case of uniform velocity, the left-hand side is fine, right? Whereas in non-uniform velocity, when the person takes turn, you have to somehow alert the system to discard the old values of the aperture and only consider the newer values. So we have to somehow know at what point the aperture has, or at what point the person has changed his direction. At that point, we will restart the aperture. That is why we call it an adaptive aperture. Okay, so we have to detect somehow that whenever the person is taking a turn, let's say on the right hand side, and from that time onwards, I have to start a new aperture for solving the equations for velocity. So how we are doing it? We are basically trying to look at the residual error of the least square fit. So in the beginning, we have shown you this equation where we were trying to solve for the velocity and the location of the person, and as a result of the drone's aperture. And now, as you see, when we try to minimize, you can always keep track of the cost function, right? All we are trying to do is minimize the cost function. And if you look at the value of the residual, right, on the right hand side, the axis we have shown, it suddenly spikes up, right? Which means that the solution is sort of getting inconsistent with our assumption, and we are not able to come down at a satisfiable solution. The solution is not stably behaving. In many cases, if there is a solution that is existent, we normally get slowly decrease the value of the least square error by this iteration and try to gradually settle down on a value. Whereas if your residual does not increase, does not decrease gradually, or it suddenly spikes up, which means that there is a red flag. So if you see, there are on the left hand side, there are lower solver residuals, on the right hand side as well, and these are high solver residuals. So our heuristic is, when we suddenly see a spike in the value of the solver residuals, there is a signature that can sniff about inconsistency of the velocity values that we are solving. Suddenly the velocity was, let's say, 1 and 2 for Vx and Vy, and suddenly it is becoming something else, 7 and 8, let's say, right? So basically the solver errors try to accumulate, and that gives you an indication that probably I have to get rid of the older part of the aperture and I have to start the aperture afresh, right? So that is how I can do an adaptive nature of the aperture. Okay, so this is the turning instant that we are detecting, and from the turning point onwards, we are going to refresh that aperture. So this helps us, this basically keeps us to the last problem. How do you solve the limited reachability? And this is more of an engineering solution, where we, instead of having a single hop solution to this particular nodes, we are trying to do this ranging on a multi-hop network. So if you actually want to implement this solution, this becomes much more challenging because the range value, the time of flight values are very sensitive. Even like 1 nanosecond change in time of flight will introduce an error of 1 foot, right? Because in 1 nanosecond, light travels 1 foot, right? So that is that sensitive, and you have to keep all these things in mind while you implement this multi-hop ranging. So in this particular talk, I'm not going to the engineering details how you implemented them because that needs a lot of background, and which is not possible in this small talk of 1 or 2 hours. So I'll just give you an intuition about how you solve the problem. So we basically try to range with the neighbors who are in the first hop, which are directly reachable from the drone, and they in turn will range the person or the node in the deep, which is deep inside the building. So instead of doing a direct ranging, we will do an indirect ranging. So drone ranges with the first hub guys, and the first hub guys range with the second hub guys, right? In this way, we are getting a relative coordinate of the node in the who is deep inside the building. And then we apply the same principles to solve for the location of all the entities inside the building. So this is hop 1 and hop 2. And this is a real deployment where we actually tested the solution. So the blue and the pink dots are actually inside the building. I've showed it on the roof just for showcasing their positions. But as you see, with a single drone who is flying outside the building, we can cover an area of about 1300 square meters, which is a lot. Right? That is the dimension of the almost 75% of the building we are covering from just by flying one drone on one side. And if you want to cover the entire building, you can have one more drone who is covering the other side of the other face of the building. Right? In that way, if this kind of a building is on fire, we can track all the people who are inside the building who are carrying these devices and also give them communication bandwidth. Okay. This is the actual picture, me with the device. I'm inside the building and walking, and the drone on the left hand side of the picture is flying outside the building and continuously tracking me inside with a precision of almost 10 centimeters. Okay, so this is the actual drone in action. It is just having a Raspberry Pi connected to a GPS, and there is an ultra wideband antenna or ultra wideband radio. You can use a different radio. You can use a Wi-Fi radio also. It's just that your precision or the ranging accuracy will be not very high. It will be like several meters, right? So of course it will give you some idea, but the accuracy of the localization will decrease, and it will depend on your application, what you need, what is the expected performance of your IoT system. That is how you should choose some modality. Okay. And this is a more close-up view of the hardware that we have used to instrument this kind of a prototype. So we just hung this kind of things, right? We just tied this to a scale and put this on top of this DJI drone, right? There is a GPS Raspberry Pi, and this Raspberry Pi controls the ultra wideband radio that keeps on ranging the devices inside. And on my head also, I have this ultra wideband radio. Right? So they two range with each other, and using the GPS coordinates that the drone is flying through, we are able to do the multilateration in real time. So this is some of the performance figures. At least what you can take away from here is we can get a localization accuracy which is less than 5 meters for most of the cases, which is pretty good in case of a situation where infrastructure is destroyed. Right? See, think about the applications where we are going to use such system. We don't need something like which is less than 1 meter. Even 2, 3 meter, 4, 5 meters is going to bring your first responder in the close vicinity of the victim, right? Then he can find him out just like that and save him, right? Rescue him. Okay, so that is just the takeaway point, that you can do pretty well in terms of accuracy in such systems. And this is a real evaluation that we have done towards the end, right? The TrackIO system was actually deployed, and just to see that how effective it is with real firefighters. So they actually carried these devices on their helmets, right? And flying a drone outside a real firefighter drill, that sort of gave us a lot of confidence that this kind of systems could be actually translated to real technology, right? It doesn't just reside in a paper and just a result of some simulations, but it's a real engineering thing that we can escalate and translate to do real prototype development, and then translate it or work with the industry to come up with the actual prototype that could be deployed, right? So this is a lot of effort that has gone inside. I did not mention the engineering details that went inside this, just the theoretical things that I have covered, and that is it. So I have covered some of the communication aspects. How can you use a drone to give actual communication where it is really needed in terms of maximizing the bandwidth, in a disaster scenario, and at the same time help these people by tracking them, right? So they need access to networks, and at the same time they need their colleagues' location. If somebody falls ill, right? Somebody has a panic attack, right? They need to be evacuated immediately, right, and taken to the hospital. So at that time, you don't want to waste time where he is unconsciously lying. Immediately, you want to get attention to that particular situation. And in our country, unfortunately, there is a lot of firefighter deaths because of the firefighter cannot find his way out. Once he enters the building, some part of the building collapses. He doesn't know his way out. So he's just trapped inside the building, and we are trying to look at technologies to help them, right? People like NDRF and all, they are really interested in building these technologies. Okay. And this from the outside, the drone commander or the person in command, right? They are called fire chief in the US. So they can actually track the location of these victims in this laptop, right? And of course, you can create a mobile app for doing all these things, doing it in a more professional way, right? So there's some research directions that I can mention, but yeah, of course, if you are more interested, you can send me an email if you want to brainstorm about this. There's a lot of opportunity of working on these drone-based systems, particularly from an engineering standpoint, like robotic standpoint, people who are actually building these drones, as well as from a mathematical standpoint, right? It's not all of them, all of the work you have to build a system. There are a lot of ways of approaching these optimization problems through simulation. For example, the trajectory optimization that I have mentioned is how do you create this radio environment map in minimum possible amount of time by minimizing your trajectory. This is a mathematical problem. Or this drone-based sensing, right? Suppose there are you want to measure your air pollution by flying a drone around in a given area. How should you fly? Where are the locations you have to put stress on? Where should you collect data from? These are more statistical problems, right? So there is a huge variety of problems starting from systems building to simulation based or mathematical exercises, algorithm development. And that's why typical IoT systems, if you see, they will have a separate kind of problem, whereas this new area of drones brings much more challenges in these IoT networks. So there are different ways to explore this problem. It's a new problem. That's why I thought I'll introduce this to you people. So yeah, I'll take questions if you have doubts about your work, or if you did not understand something, I can explain. With this, I'll complete the talk.
Hello, participants. If you have any query, you can ask or you can raise your hand. Okay, I think nobody has any query because, sir, you have presented very nicely. So I think most of the doubts are cleared. Okay, so anybody is trying to say something?
Shamapada.
Yes, sir. Yes, sir.
Yeah. Actually, I don't have question, but I'm very, very, excited hearing such an excellent work.
Yes, sir. Yes, sir.
So, yeah, such an excellent work. Thank you. Thank you for presenting, and that too, you have presented so nicely. I think those who are present here, hearing you, they will able to understand everything.
Oh, thank
I
you,
have a
sir.
small query. I have
Yeah.
a small query. When someone is inside the debris,
Mm-hmm.
a building has collapsed. Someone
Okay.
is inside the debris. So how this particular tracking system will be effective in that case?
So there are technologies of the wireless modality we are choosing that can travel through the debris, right? If it is a lot of concrete, it is not possible because the wireless signals will get blocked. But if it is like a few bricks or maybe one layer of concrete, we can use things like Wi-Fi, which can go through them.
Okay. Okay. Actually, Sharma, it's remind me, actually, our project.
Yes, sir. Yes, sir.
Yeah, actually, whatever you have been telling in the name of, disaster, actually,
Yes.
Northeast, there are plenty of areas, where
Right.
accessibility during normal period itself is very tough.
Right.
So,
Right.
so there basically we thought of doing something using similar kind of concept, using a drone for
I
that,
see.
and getting some information and doing something. So thank you for your presentation. Excellent presentation and excellent work. By the
Thank
way,
you.
are you starting a company?
Actually, yeah, I have left my parent organization, so I don't. We have the patents done, right? So there is a company that we have started with this Track IO, but I'm not a part of it anymore.
Okay.
Yeah,
Thank
because
you.
I have
Thank you.
lost all the rights and come to India.
Yeah. Okay.
Sir, actually, as Professor B.K. Roy sir told that we are also like having some plan to do some kind of this kind of work. Okay.
Okay. Yeah.
So is there a possibility to collaborate with you?
Absolutely. Yeah. I'm trying to set these kind of things up in the systems domain, right, in India, because here we don't have a lot of players actually building things.
Yes.
So yeah, definitely.
So we will contact you again. Okay, regarding
Yeah. Sure. No problem.
proposal and all. But today, sir, you are splendid. You presented very well, as sir said, and I think every participant will appreciate it and they learn many
Yes, yeah.
things.
If you have any questions, anybody, you can just write me an email. If you want to discuss, I am open to any discussion.
Okay. So thank you, sir, for giving
Thank
your
you.
time, valuable time.
Yeah. Thank you,
Okay.
everybody, also for
Thank you.
inviting me. Yeah. Thank you. Yes. Okay. So I'll close this thing, right?
Yeah. You can leave the meeting now, sir.
Leave the session. Okay.
Okay, participants, we have another session now. So just let me see whether the expert is ready or not. Let's do this now. So next we have Professor Devdeep Mukhopadhyay from IIT Kharagpur. So he will be talking about some security issues in IoT and all. So let me call him. Then I'm coming back.
Hello.
Hello.
Yeah, can you hear me?
Yes, sir. Yes, sir.
Okay, so how do I present? Should I share my screen and start?
Sir, actually, can you on your video? I cannot see you.
Okay, yeah, I hope it works. Let's see. Can you see me now?
Still not, sir.
The camera is showing on. Can you see me? No.
No, sir. Still not. Anybody, any other can see, sir?
Okay, let me just.
We can see, sir.
Okay.
Okay. So, sir, just let me introduce you. Okay. So,
Sure. Yeah. So maybe I'll just share the screen once.
yes, sir. Now you are visible.
Can you see my screen?
Yes, sir. Just a minute. I will share your profile and
Okay.
as a,
Okay, so I'll stop sharing.
yeah,
Okay.
virtual felicitation only.
Okay. Yes, so I think you can share now.
Yes, sir. Yes, sir. Okay, so dear participants, we have our next expert, Professor Devdeep Mukhopadhyay from IIT Kharagpur. So we are very happy that he is with us now. So Professor Devdeep Mukhopadhyay is currently a professor at Department of Computer Science and Engineering, IIT Kharagpur, India. At IIT Kharagpur, he initiated the Secured Embedded Architecture Laboratory, SEAL, with a focus on hardware security. He had worked as visiting scientist at NET Singapore, visiting associate professor of NYU Shanghai, assistant professor at IIT Madras, and as visiting researcher at NYU Tandon School of Engineering, USA. He holds a PhD, an MS, and a BTech from IIT Kharagpur, India. His book include fault tolerance architectures for cryptography and hardware security, Springer, cryptography and network security, McGraw-Hill, hardware security, design threats and safeguards, CRC Press, and timing channels in cryptography, Springer. He has written more than 200 papers in peer-reviewed conferences and journals and collaborated with several Indian foreign organizations. He has been in the program committee and editorial boards of several top international conferences and journals. Professor Devdeep is the recipient of Sarnajwati DST Fellowship 2015-2016, Data Security Council of India Award for Cyber Security Education, ACME Duo Fellowship, INSA Young Scientist Award, INEE Young Engineer Award, IAS Young Associateship. He was awarded the Outstanding Young Faculty Fellowship from IIT Kharagpur and the Techno Inventor Best PhD Award from the Indian Semiconductor Association. We are welcoming you to this course, sir. So we are virtually doing this course, so this is a virtual felicitation to you. Thank you, sir, for joining. You can proceed with your lecture, sir. Thank you.
So thank you, Dr. Shamapada, for this kind introduction. So, and thank you all the organizers for inviting me for this talk. So let me try to share the screen. I think you have to stop sharing probably. I don't know.
I have stopped, sir.
Okay. Somehow my sharing privilege is not coming up. Okay, so let me. I'm unable to share my screen. Actually, it was working fine.
It's not okay now.
It is not allowing me to share my screen. Can you share my see? You can't see my screen right now.
No, sir. Only your camera is on.
Yeah, the shared option is not enabled actually. So I don't know.
But every privilege is given to all the participants.
Hmm?
All the privileges are given to everybody here in this meeting.
Yes, but yeah. So have you stopped sharing at your end?
Yes, sir. I have stopped.
Okay, in that case, let me just log out once and try to get back again once.
Okay. Yes, sir. Now it is visible.
Mhm. Okay. So can you see my screen now?
Yes, sir. It is
Okay.
good.
Okay. So thank you very much for this introduction and the invitation. So I have roughly 2 hours, right, for my talk. Like it starts from 3 and it ends at 5, right? I mean, if I'm
Yes.
correct.
Yes, sir. Yes.
Okay. So in that case, right, I will try to give you an overview of some of the aspects of security in the connected world, and I will be trying to, like address some of the important aspects which crops up from the underlying hardware usages at various ends in our connected world. So it will be a relatively long session. So I would be requesting you to, like, please feel free to interrupt me, and if there are any questions at any point, I would like to be happy to address to them. So in this work, I mean, the agenda of my talk will be roughly divided into these 4 components. The first part, I will be trying to talk about the background. Like essentially here, I will try to kind of give a bit of overview on some of the works that we have been doing at IIT KGP. Specifically, our laboratory, which is called as Secured Embedded Architecture Lab. Then I will try to focus about IoT or Internet of Things and talk about one important aspect, because we know that crypto algorithms or cryptographic algorithms are implemented to obtain end-to-end security. And when you implement cryptographic algorithms, there are some small avenues for attacks, which essentially can lead to disastrous consequences. These are called as side channel vulnerabilities, and the attacks are called as side channel attacks. So specifically, I will be trying to talk about 2 important attack vectors, which are called as power attacks and fault attacks. Then I will try to kind of shift my focus towards the problem of authentication of devices, which means we know that now it is envisaged that billions of devices are communicating. So how do you trust these devices? And these devices need to talk to each other, communicate important data. So while you can adapt classical crypto systems, but often they are very complex, and therefore, right, people try to look for lightweight solutions for authentication. So I will try to talk about specifically a hardware security primitive, which is called as physically unclonable function or puffs in this context, and try to see how potentially we can develop authentication protocols using puffs. And finally, if time permits, I will be trying to talk about I would say, like the final frontier of the IoT, or the other side of IoT. Like on one end, probably you have got resource constant devices, while on the other hand, you have got more powerful computing resources, which are often called as cloud. So the cloud is typically a heterogeneous platform where several parties can, like work, and essentially the idea is that you can do computation on shared resources. Many times this actually leads to concerns about security and privacy, and we shall try to see that how we can probably address such kind of concerns by applying encryption. But these encryptions are specialized encryptions in the fact that while they encrypt, they still allow some kind of analytics to be performed on the cloud. So usually, like suppose if you are interested to do, say, a search on a cloud database and you still want to keep the data encrypted, then how do you really, or is it at all possible to develop such encryptions which are amenable to such kind of operations? So, with this background, let's start. So this whole topic of embedded security essentially tries to look into the gap between theory and practice. If you take any standard textbook, classical textbook, which talks about cryptography, you will find that these are usually the parties that are involved. So usually there is a sender and a receiver who are legal users. Say we call them often as Alice and Bob. And now there is they essentially want to kind of communicate some information over an untrusted channel, and this untrusted channel is often targeted by a third person who is not necessarily a legitimate person. So in this diagram, it has been shown as a malady. So if Melody is, for example, curious to know the information, or maybe like modify the information that has been communicated from Alice to Bob, then what Alice and Bob often does is they try to apply some kind of cryptographic techniques. So these cryptographic techniques typically takes the input and converts this into a sort of a gibberish text, which is hard to understand from Melody. And using certain principles or primitives, it often also tries to kind of ensure that any modification that Melody does, right, is detectable by, say, Alice or Bob. So this is the classical picture of cryptography. However, we know that when we talk about real life implementations, then there are often, like various limitations. And because of these limitations and absence of theory for the reality, even mathematically strong ciphers would leak in the real world. So if you are, for example, relying on a very strong cryptographic algorithm like, say, RSA or AES or any other well-known algorithm for that matter, but if the implementation is not suitably done, then it can lead to like interesting attack vectors, which are often called as side channels. So side channels are information sources in the real world through which a cryptographic module, like suppose if you take a crypto algorithm and if you implement it on some kind of like either software or maybe on a hardware device, then it may still leak information to the environment, often in an unintentional fashion. So for instance, like the power consumption of the device, the time required to do a computation, and so many other like possible manifestations, right, or information leakages can lead to the complete collapse of the crypto system. So how do you handle them? That is essentially the target. So in a nutshell, and like in a lighter note rather, so we know that in theory there is no difference between theory and practice, but in practice there is. So I often use this example to sort of again illustrate my point. So this is essentially a very popular e-locker that we often like use in our day-to-day life. You see them in hotels and so many other places, where the idea is that there is a locker and you essentially, it is expected, or the security designers of this locker expected that there is a 6-digit pin, and if you only know that 6-digit pin, then that locker will open, else it will not open. So as a fun exercise, we try to like buy this one of these lockers and did an exercise where we found that if you open up the front panel of the locker, which is not very difficult to do, and we identified that there are two pins inside this circuit. One is the reset pin and the ground pin. Apparently, if you contact them or connect them together, then the pin gets zeroized. So this like is a very simple example to show that there is often a gap between what you essentially design and what you practice. Now it is probably not much difficult to make this design circumvent this weakness, but the point is like how do you test your devices and how do you unearth so many possible weaknesses that can be there in systems, okay, and which essentially, if they are not detected during the design phase, right, can percolate down and get into your products and lead to a complete break of your system, even though you had essentially very nice mechanisms to protect. Because an attacker never enters your system through the strongest path, but it tries to kind of get in or sneak inside using the weakest path. So this kind of emphasizes again, like the importance of suitable implementations of cryptographic principles or security principles to ensure that the leakages are as minimized as possible. So in order to do this kind of research on various kind of attacks and countermeasures, nothing to do with the US made in seal, but it is just an academic endeavor where there are several faculty members, postdocs, and research scholars. This is a small sort of picture out of the entire family, which tries to kind of work in this domain of finding out new attacks and suitable countermeasures. So one of the important aspects of our line of research is to experiment and really see that whatever theory that we are trying to develop works in practice. So instruments are therefore a very important aspect of our line of research, where we try to, so here are some pictures to show you a sneak into our laboratory setup. Like you have got like laser stations, side channel setups, and temperature chambers for like evaluation. Recently, we are trying to work in hardware forensics, where we have established a scanning electron microscope and a FIB, which is a very powerful instrument to look into inside your IC chips at the resolution of 10 nanometers, and we are trying to build on that to see how we can develop techniques for hardware forensics. We also have a laboratory for IoT setup, where we try to look into the various vulnerabilities that IoT devices can have. Recently, we are also trying to venture into cyber physical system security. So here is a kind of a picture on a basic smart grid setup that we are trying to build up. So there are various ongoing security projects in our laboratory. So one is on, of course, like we are working on the traditional hardware security problems. We are also trying to look into post-quantum security. We know that the quantum machines, right, when invented, can put to threat several public key crypto systems, and therefore, like there is an ongoing research on developing post-quantum techniques. So one of the key challenges with respect to post-quantum is to make suitable and efficient implementations, and we are also trying to do so. We are trying to look into cyber physical system security, Trojan design detections, and anti-counterfeiting, malware and ransom detection, ransomware detectors and detections, and so on. So with this brief background, right, I would like to kind of mention that again, like kind of stress that one of the reasons why security is often missing in our day-to-day products is because often security products are too root, and we often feel that they are root, in the sense like all of us want to be secured, but nobody really wants to pay for security, and security measures are often overkill, and therefore it is missing in our thought process. So therefore, it is a key objective of security designers to ensure, first of all, to understand the threats, and then to develop systems so that the systems are efficient at the end of the day. Because even us, right, when we go to buy a computer in the shop, our first requirement is performance, right? I mean, security always comes as an afterthought. However, because of the growing, like connection between devices, and when we talk about IoT, cyber physical systems, then security is getting more and more important. It is getting paramount important, and therefore, right, it is important to kind of blend security right now, right from the beginning of your design inception. So, so therefore, right, and we cannot say, like that we are ignorant about security. So here is an relatively, I would say, now dated sort of report to show that there are large financial losses which occurs because of cyber attacks, and therefore, right, it is important to fortify our systems against such kind of attacks. So we all have heard about these powerful attacks like ransomwares, which essentially are a class of malwares which tries to encrypt your systems. And even recently, right, there are reports of ransomwares hitting several medical devices, critical infrastructures, and then the idea is that the attackers try to kind of ask for the victims to pay for the decryption key, because the moment decryption key is available, then only they can kind of decrypt and obtain back the files. Now, when you pay your ransoms, whether you will get it or not get your files is completely at the mercy of the attacker, and therefore, right, it leads to huge amount of cost. So this is the kind of, this is a diagram from, this is a snapshot from one of the very lethal ransomwares that hit around in 2017, which is called as the WannaCry. So I hope that none of you have seen this on your computer screens, which basically tells that your files have been encrypted. And once you encrypt, then as you can see that in order to recover your files, it asks for money to be paid. Okay, and only if you pay it, apparently it will give back your data, or it may not give back your data. So you can see that these ransomwares had hit around, like say more than say several lakh business across to almost like 150 countries, and you can easily see in the map that India was also not left out from this menacing threat. So attacks have become more and more powerful, and when we talk about attacks on IoT and critical infrastructures, then one of the most classic examples that is used in this context is in the context of what is called as Stuxnet. So this attack essentially is targeted something which is called as SCADA, or supervisory control and data acquisitions, which is nothing but a system of software and hardware elements that works with your industrial cyber physical systems. So their objectives are to control the industrial process, monitor, gather, and process the real-time data, and to directly interact with several actuators and devices like valves, pumps, and motors. So in this attack, which is a very classical example of how very simple attack vulnerabilities can lead to disastrous consequences, in one of the Iranian nuclear power stations, which was engaged in uranium enrichment facility, near their premise or near their office or near the laboratory, apparently, right, some people were selling USB sticks at a very low cost, with the objective that one day or at some point, some of the members who are working in that enterprise will fall trap and will buy those USB sticks, which were injected or infected with a malware. So now, say, imagine that one of those guys uses them, and then the malware essentially enters the Iranian computer systems, and it tries to search in the industrial control system to find out that whether it essentially can connect to a computing system which is essentially used in their strategic operations. So the strategic operations were certain computing systems which are used to run high-speed centrifuges. So centrifuges are essentially this revolving, say, you can think of the actuators to enrich nuclear fuel. And when it is able to do so, that is, it finds out its target, it downloads a more recent version of itself to ensure that it is not detected by simple malware detectors, which often does static analysis. And then it tries to compromise the target's logic controllers, and it starts to inject small perturbations to the internal state, ensuring that the online detectors which are present in the cyber physical systems of these like nuclear power stations, they are not able to detect the small variations in the system state. So gradually, right, I mean, the Stuxnet or the virus spies on the input output of the control system, and then it starts to spin the centrifuge with small perturbations to ensure that they are not being detected by the online monitors. And finally, when essentially it provides a false feedback to the output controllers, it keeps on doing this, and finally, right, when it is detected, then it becomes too late. The centrifuge starts to rotate at an enormously high speed, and then it leads to a complete breakage of the entire system. So this was a very powerful malicious computer worm, essentially being one of the reasons for this attack on the Iranian uranium enrichment facility, and it was not detected by any of the popular antiviruses like Kaspersky and so on. So this tells us, like the kind of connection between your cyber physical system security and a small malware infected USB stick. Okay? So therefore, right, we need better and smart techniques to understand how do you really know that such kind of systems are not crippling your CPS systems. So another killer application when it comes to cyber physical system security is this example of automotives. We know that today's modern cars have become more and more connected, and every car is probably more has larger pieces of code programs compared to maybe even a computing system. So this is an example that was published in Wired in 2016 and presented at Black Hat Security Conference. So here it shows that there is a car which is, say, running on the highway, and it shows that just on a very top level, if that it turns on, right, I mean the Jeep's radio, and the attacker essentially tries to kind of rewrite the code which is embedded in the infotainment system. And the objective of this small modification is that it is able to, or the attacker is able to kind of issue commands through the internal network to the steerings, brakes, and the engine, so that in the middle of the ride, right, suddenly the car is possessed. So as you can see in the top diagram, the gentleman sitting over there is showing that his car is basically being possessed, and he has no control over the car. And therefore, you can imagine that somebody can create an, like an accident without even us being able to control. So this is a classic example of a remote hacking of cars. Okay, so this shows that even our automotive systems, which are usually connected with safety, has now a very strong linkage with security. So in one of our research in our laboratory, where we worked with a company called Bosch, we tried to publish this paper in date 2020, which shows how, or so this is an example of this diagram that you can see over here is a very classic depiction of the control system, where there is a plant, there is a controller, and there is a detector. So now what the attacker does essentially is trying to kind of modify the output of the plant and the controller in a manner so that the detectors are not able to understand that the difference essentially is being created by the adversary. So as you can see over here, the detector tries to kind of measure a difference between the output of the plant and the controller's output and ensure that the absolute value of that is always smaller than a decided static threshold. So now the attacker understands this policy of detection, and it tries to kind of inject perturbation so that the condition of the detector is never violated, and therefore the detector doesn't throw any alarm. But then can this stealthy attack bypass and create like a havoc? So here is a simulation which shows that it indeed can. So you can see here that the system state shown here by the blue line essentially is gradually increasing, and it crosses the safety bound in certain amount of time. Whereas if you see the residue, which is shown by the purple line, is never exceeded. Okay, so this shows that it is possible to kind of manipulate data if you are not taking any suitable protection in your cyber physical systems, so that the overall security or the overall like the safety bounds of your systems are completely violated, whereas the online safety detectors or the online monitors are never like bypassed. So therefore this shows us that when you talk about security and when you talk about safety, there is a difference. Safety is a different objective and security is a different objective. Because when we developed our systems and we talked about safety so far, when we talked about fault tolerance and so on, we were really bothered about safety against attackers. We were really bothered about safety against like natural faults or natural disasters, which is not biased. On the other hand, when you talk about attacks or when you talk about malicious adversaries, then they are always biased and they have more intelligence to essentially create perturbations which are not detected by the online mechanisms or by the safety mechanisms. So we need specialized protections. So here is another classic example, which is essentially, I mean, some of you may have heard about this, which is called as Spectre and Meltdown. And Spectre and Meltdown essentially falls under the class of attacks, which are called as micro-architectural attacks. So the micro-architectural attacks essentially are another very powerful. So this was a paper which was published in Google Ground Zero project, which essentially is another very powerful class of attacks. So I will try to give a very top level understanding about what these class of attacks are. So all of us are using some form of computing system, right? So maybe we use working on a workstation or we may be working on a laptop and so on. So these computing systems, right, I mean for the last 20-30 years or even more than that, has got several improvements like which has been incorporated to enhance the overall performance of your system. So one of these essentially like is a very like popular form of architectural feature that is present in our computing systems is what is called as speculative execution. So speculative execution, simply put, what it means is that when it tries to say for example, imagine that there is a branch statement in your program, okay, and the idea is that you may wait for your branch to get resolved, and then the processor may allow you to go ahead and do certain executions, but that would take a lot of time. And therefore, our modern day computing systems, they speculate based upon, maybe in this case, an output of a branch predictor, and it tries to kind of take some steps and do some operations. And later on, if it finds that the resolution was wrong, it basically undoes those statements and again repeats it. But there is a small security glitch over there, which was overlooked for say the last 20-30 years. So although like when you are, suppose you are, like suppose imagine that there is an if statement which essentially is dependent upon a password that you are entering, and maybe like you enter a wrong password, and therefore, right, ideally what we expect is that you should not be accessing say some important files, but your computer system underlying, right, does those executions, and later on when it finds that you have entered the wrong password, it undoes that, and it basically doesn't allow you access to those systems. But internally, since the computer had performed certain maybe memory access and so on, that data, right, essentially gets put into the cache. Okay. So for example, right, you may imagine that it tries to access a specific region in the memory, and although eventually when it finds out that the password is wrongly entered, it tells that, okay, you do not have access to this part of the memory, but the attacker, who is intelligent, knows that internally the computer had accessed, and therefore this data should be present in the cache, and tries to go and read out the cache content. And there are many techniques how you can do that, and through that it tries to get your business critical documents, your critical informations, and so on. So Meltdown and Spectre essentially falls into that category of attacks, which tries to kind of show that when you are doing your computations, right, it can lead to the like the revelation of your very critical data, like it may be your business critical documents, your credit card informations, and so on. So how do you prevent against these attacks? And to quote Bruce Nair, who is a very famous security reporter, he says that fixing them requires a patch that results in a major performance hit or is impossible, and requires a re-architecture of conditional execution in future CPU chips. But that basically means like going back 20 years and then coming again forward. So therefore, right, this is not, so these class of attacks, which really doesn't break a crypto system, but tries to look for like several accessory avenues, are often classified as what are called as side channel attacks. So in this case, this side channel attack works by manipulating the branch prediction and the speculative execution of your present day computing systems. So therefore, as I said, side channel attacks tries to address this gap between the theory and the practice. And if you think that this problem can be solved by cryptography, then we do not understand either cryptography or the problem. Okay, so it is not really about adopting cryptography, but it is really about how you implement cryptography. And there can be various sources of side channel information. So like when you talk about security, then there are various parameters that essentially comes into mind. So when you talk about real world systems, then you have got the threat model and the security goal. It is very important when we start developing an attack or developing a countermeasure, then we have to properly articulate the threat model and the security goals of the adversary. Traditionally, we have been handling the cryptographic algorithms, the protocols, the software implementation, the hardware implementation, the usage, the development, and finally human users. Okay, so I will be very like naive to say that it is impossible to design a totally secure system with humans in it. So we'll not even try for that. And there are actually like a bunch of people who tries to look at that aspect, and I think that's a very important line of research. But what we are really bothered about, like traditionally we have been handling about crypto algorithms, but the software implementations puts in like or gives rise to key dependent variations, computation time variations. The hardware implementations have got several manifestations like power consumptions, EM radiations, test methodologies, behavior under faults, and so on. Some of this we will try to look in our discussion. So the message is that strong cryptographic algorithms are just the beginning. You can take a very strong cryptographic algorithm, and if you can implement it, you will find that there can be still weaknesses. So you can imagine that there is a smart card that you have, and you take your car to the nearest, like petrol or diesel station, and then you access your credit card. So you put that into some card accepting terminal, and then you exchange the inputs and outputs. So if you have got a strong crypto algorithm, say an RSA or an elliptic curve, then when you are exchanging input and the output, then you are pretty happy that the mathematics behind the algorithm is ensuring that your secret key is not revealed. But in real life, it may happen that the power supply, okay, maybe the power, I will try to talk about, like how that happens, okay. But in this case, if you observe this power consumption graph, which is taken from a microcontroller in our lab, you will find that there are very distinct spikes, okay. Now, all the spikes are not of the same type. You will see that there are some spikes which are very thin, and there are some spikes which are a little broad, and they are because of the fact that when this broad thing happens, that means that your device is essentially performing some extra computation compared to the cases when you have got a very thin spike, when that computation is not being done. So the idea is that the computation that you are doing is dependent upon the underlying data that you are processing. It depends upon the underlying operation that you are doing, and that leads to often, like if you are not taking care of your implementation, straightforward reading of the secret key. Okay, so the thin spikes are corresponding to, say, zeros, and like the broad spikes are corresponding to 1, and therefore some attacker, right, who is knowledgeable can just observe this trace, and from there can directly leak and obtain your secret key. So therefore, right, you need protections, and security can indeed be a game changer. Just to motivate what I said just now is, let's take a little look back at Intel stock. So when this like this meltdown and Spectre attacks were surfaced, then Intel beared most of the fallout after somehow, like its rival AMD had a like a better performance against these attacks, and therefore Intel stock really fell significantly down, around like something like a 3% decline compared to what it was initially. So this says that security can be a game changer. So this is the like the link from where I got this statistics, but it tells us that security has started to become an important game changer, okay, in terms of not only like the academic world, but in terms of the real industry world, where like absence of security can lead to like large financial and like even other humanitarian loss. So this brings me to the end of my first part of the talk, okay. And if there are any quick questions, I will be happy to answer, or I will go ahead with the next part of my talk. Any questions so far? Am I audible?
Yes, sir. Yes, sir.
Yes, sir, you are audible.
Okay. So if there are no more questions, then let me go into the second part of my talk, where I try to talk about sidechain attacks in slightly more details. So we have been talking about IoT. I think one of the like stretches of like this workshop is also on IoT. So we know that IoTs are expected to extend our Internet of Things, and we know that there are several billions of devices which are expected to be communicated and connected. So while IoTs can revolutionize the quality of life, but commercial IoTs, the IoT that we buy from the market, often lacks security measures, and it can really have bad consequences. So let us try to look at, first of all, the good part. Like IoTs can really have got like strong applications. Even in the Indian context, It can lead to good water control, food control, protections against natural disasters, e-governance, pharmaceuticals, and like nowadays, like is probably really important when we talk about like counterfeits and in drugs, maybe in vaccines and so on. Maybe IoTs can really help to like revolutionize the quality. But it is important to integrate security into the IoT by developing novel security protocols for interactions of multiple components which are secured against menacing threats. So I will try to talk about few of these important threats that have been talked in literature. So let us start with this famous paper which was published in IEEE Symposium on Security and Privacy, which is one of the top conferences in security and privacy, by this Israeli group led by the great Shamir. So Shamir is like, for some of you, right, who are not aware, like RSA, right, Shamir stands for Shamir. So in this work, so this work was essentially trying to demonstrate the vulnerability of some of these IoT huge systems or light, like light automation systems, which was commercialized by Philips. These are called as Philips Hue lamps, and they are used for like automatic control, and you can think of like they are used for home automation, which means that they are being deployed in the offices and in the premises of some. So in this case, as you can see in the top diagram, it shows these bulbs being deployed in the Israeli companies, and there are very famous company names, as you can see, and they are being deployed in the office premises. So the idea of these bulbs is that only you as a user should be able to control and command, but the adversary, who is probably like driving down the road, should not be able to control and command those bulbs. So one of the reasons they are not able to control and command is because of the fact that there is a proximity detector in the like embedded systems on like I mean of these bulbs, where through which it ensures that people far away should not be able to control these bulbs. And also, right, these bulbs are authenticated by, and there is a whitelist that is maintained, and anybody, right, who essentially cannot provide that authentication token should not be able to control and command those bulbs. So therefore, right, these are so now what we will try to kind of see in this paper is that it shows that the security system for these bulbs can be bypassed by a technique which is called as correlation power attacks, or CPA. So the idea is that the attackers first of all wanted to kind of bypass the proximity detector, and in order to do that, they wanted to modify the firmware of one of these lights that are being deployed. Okay, so they went, for example, inside this office, and then they took physical control of one of these bulbs, and they wanted to update the firmware. But then anybody cannot update the firmware, because when the firmware is updated, and if you want to again put that back and re-execute it, there is a security technique which is called as like AES-CCM, which is essentially the idea is an authenticated encryption. That means there is an encryption being done and there is an authentication being performed using the AES block cipher. So there is a secret key that is involved, and the secret key is, say, a 120-bit key secret. So of course, right, the attacker cannot guess the 120-bit secret. So the attacker essentially took attack or CPA. So what the attacker does is it allows the bulb or the firmware of the bulb to perform essentially certain encryption operations, and when the encryption operation is being done, it tries to kind of obtain the electromagnetic trace of the around the device. How do you do that? I will try to talk about that a little later. And once these EM traces are being captured, it performs an attack method which is called as CPA or correlation power attack. And using that, it tries to get back the 128-bit key secret. And once the 128-bit key secret is obtained, it can basically modify the firmware, and you can think of like it can sign the like the changed firmware by the secret key, because now the attacker knows the secret key. And therefore, one of these bulbs now essentially has got a modified firmware in which the proximity detector has been bypassed. And then what they do is even more interesting. They now use these, remember that these bulbs are connected with each other in the office premise. And then they show that how a self-spreading worm, essentially using the combined ability to sign and encrypt arbitrary binaries, can like perform a nuclear sort of reaction in the IoT systems. So basically the idea is that one bulb infects a few others, and then again those bulbs affects even further. And then they show a phenomenon which looks like IoT goes nuclear to justify the title. So there is a very interesting demonstration you can see right on YouTube, where they show that they take few drones, and using the drones they basically control these bulbs, and then they display an SOS at their own disposal, so at their own discretion. So this shows that the IoT systems, essentially like at least a popular IoT system sold by a very famous company, right, also essentially can have vulnerabilities, and often these vulnerabilities arises because of a wrong implementation of the crypto algorithm. So there is an authenticated encryption being in place so that the firmware cannot be updated, but the way in which the implementation was done did not take into account that an adversary can take physical possession of those devices and then recover the secret key by applying techniques which are called as side channel attacks. And once the key is revealed, right, it can update the firmware and essentially can jeopardize the security assumptions. So therefore, it is important to ensure that your crypto devices do not have such kind of glaring vulnerabilities. So therefore, right, talking about what are side channels, I mean, we know that, like the side channels essentially, so this is a sort of an experimental setup that we have, just to kind of show you, like how a side channel setup will probably look like. So the side channels essentially, so in this case, you can see here that there is a device which being shown in the down. So it's essentially, this is a device on which, say, you are running a crypto algorithm. So it could be an FPGA device, it could be a microcontroller, or any other target where there is a crypto algorithm executing. So it could be a DES, 3DS, RSA, elliptic curve, anything. And when the device is communicating, there is essentially a PC which is say sending input packets, and the device is essentially encrypting, and the cipher is again brought back to the controller PC. Now when this execution is being done, there is an oscilloscope which is observing the power traces, and it is essentially is bringing back those power traces back to the PC. So therefore, at the PC end, you not only have got access to the classical input output of the cipher, but you also have access to, say, the electromagnetic radiations or the power consumption of the device. And the question is, right, using these power traces, as we say, can you recover the secret key? So these are some real life pictures of the oscilloscope and your target device. Okay. So therefore, right, the power attacks. So talking about power attacks, or like any like these classical forms of side channel attacks, you will see that largely they are divided into two types. One which are called as simple side channels, and the other which are called as a differential power attack. Whereas the simple side channels attacks are much more convenient to perform. So the fact which is reasonable, which is responsible for leading to simple side channel attacks or simple power attacks are because of the fact that the power consumption at an instance of time is a function of the operation being carried out by the device. Okay. So let me give an example to illustrate this point. So, so when we talk about, so let me talk about an example to illustrate this point. So imagine that if you have got an, algorithm like RSA, so this is just, without loss of generality, I'm trying to give an example. So if you have got a crypto device, which is say performing a decryption, so imagine that you are giving the cipher and there is a small key being stored inside, and that is your decryption key, say D. And you are passing the input, say as Y. So what this chip does now, or this software does, is it basically computes Y power of D. Okay, so it performs Y power of D, and it of course does a modulo operation with say some mod of some public parameter. So the attacker is curious about what is this information D, because the attacker wants to know the secret key. So usually when you perform this Y power of D, you don't multiply Y D times, right? Because that will essentially be very inefficient, because D can be really, really large. D is often, when you talk about RSA, we are dealing with say, 1024 bit or 2048 bit arguments. So that D can be really, really large. Okay. So what we therefore do rather is we say perform something which is called as a square and multiply algorithm. So in square and multiply, the idea is that you don't perform Y power of D, but you essentially write down D as a binary. So you take the D, okay, and you express this in the form of strings of ones and zeros, maybe 1, 0, 1, and so on, and you express this in some binary notation. And then you start observing what are the key bits. So the implementation basically looks at the key bits, and the idea is that if it is a 0, so it always, the idea is that it takes a register R and it initializes R to Y. Okay, so it makes R equal to Y, and if, or this bit is 0 or this is 1, independent of that, it basically performs a squaring of R. So it calculates R square. And if this bit is 1, then along with R squared, it does an extra operation of multiplying this R square with Y. Okay, so pardon my bad handwriting. So basically, it multiplies this R squared with Y. So note that this operation, that is this extra multiplication, is being done only when there is, when your secret key bit is 1. Okay, and now if you look at what is written over in this slide, it says that the power consumption at an instance of time is a function of the operation being carried out by the device. So that means the power consumption of a multiplication operation and the power consumption of a squaring operation are different. Okay, and therefore if the attacker is able to pick up that difference from the power trace, then the attacker knows that there is an extra multiplication that has been done, and because of that it also knows that whether the key bit is 1 or whether the key bit is 0, because when the key bit is 1, only then this additional multiplication is being done, and therefore, right, the attacker knows the secret key. So therefore what the attacker now does is it basically looks at the power traces and sees that whether the power trace is a narrow power trace, or it's basically depicting that there is a less power being consumed, or whether the power consumption is large. Okay, so in real life, you can actually try to kind of automate this process by applying some kind of pattern matching and machine learning and so many other things. But at the bottom line, this is what is happening. Okay, so that means that the power consumption, right, is, since it is dependent upon the underlying operation, and if you are implementing it in naive manner, which is not really naive because it's one of the most popular ways of implementing exponentiation, which is called as a square and multiply. Okay, and but that leaks. Okay, so therefore this is an optimization that you are doing to make your implementation more efficient, but the same optimization is essentially leading to the leakage of your secret key. So the question is, right, how do you really ensure that your design will be efficient but still will be secured against such kind of leakage sources? Now there is another very powerful form of like ensuring that irrespective of whether the key bit is 1 or 0, you will say always do a dummy multiplication. Okay, so that kind of tries to balance the power values, and therefore the idea is that the attacker will not able to distinguish whether the key bit is 1 or 0 by just observing at the power consumption. But then there is another very powerful form of attack, which is called as differential power attack, which essentially is still based on even more fundamental reason. So it tries to kind of exploit the fact that the power consumption depends upon the underlying data that has been processed. Okay, and this is even more fundamental because now, irrespective of the fact that you are always doing, say, a square and multiplication operation, right? Still, the attacker using the power values can try to correlate and obtain the underlying data that your registers are storing. Okay, and note that the designer of the algorithm, whether it's a public key algorithm or a block cipher, okay, wants to ensure that the attacker doesn't see what is happening internal to the crypto algorithm. Okay, but rather the algorithm wants, or the designer wants, that you as an attacker should be only seeing the output of your computation, okay, of your ciphering computation. So therefore, right, if the attacker is able to get some internal information, then the attacker ideally, right, should be able to narrow it down and get back to the secret key. Just to give another example, so that when we talk about the AES algorithm, the designers want that I will take a plain text, I will take the secret key, and then I will do internally 10 rounds to give you the corresponding cipher when we talk about AES 128. But using side channels, you potentially can get the output of the first round. Okay, and therefore, right, once you get the output of the first round, it is very trivial to use that with the plain text knowledge to get back the secret key. So these are very simple, like sort of examples. And this study originally started from this famous paper published by Paul Kocher, Jaffe, and Benjamin Dunn in Crypto in 1999, and essentially started the formal study. So actually, there was another paper in 97 where he talked about the timing attack, and this was more on the power attack part. Okay, so this is a power analysis work. Okay. So any questions on this point? Should I continue?
Anybody have any question?
Okay, so let me continue then. So therefore, simple.
So one student wrote one question, sir.
Okay, sure.
Question is there any database which stores these power spikes?
Database for power.
Power spike.
Okay, so database means if you're asking like, is there any like central database for doing research on such kind of things, right? Then there are actually some databases that are present nowadays. So there is one database called as ASCAD dataset, ASCAD. So if you are interested, right, you can take a look at that. Let me just try to write it here. It is called as ASCAD. So it comes out with several power traces, which you can see, and you can like experiment on these techniques. Okay, there are one or two more, but ASCAD is a very popular public repository of power traces. Okay. Any more question? Okay, so let me continue. In that case, right, I mean, I was talking about, so simple power attacks, essentially, as I mentioned, tries to basically see the power trace and directly interpret and get the secret key. So this basically tries to operate on few traces. So it could be maybe one trace or maybe 100 traces, but not more than that. So trace, when I say a trace, right, it basically means the power consumption. So you can think of them as, like suppose this is your time domain and this is your, like this axis is the power or the current. And typically when the encryption takes place, you are essentially, this is your power profile. But using a very good oscilloscope, right, you try to kind of sort of sample this power trace at a specific frequency. So it has to have a high storage capability. And typically, just to give an example, say if you have got 1 millisecond operation, which is sample points, will basically points which you are like breaking up your encryption time. So suppose your encryption time takes a t amount of time, you are breaking that out into t by 5,000 time instances. Okay, So therefore, right, this is an example of a power trace. So you can see that this is an example of, in fact, the AES power trace. So you can see that seeing the trace, right, you can understand, you can virtually read out the fact that it has got 10 rounds of encryption. So you can count, like these glitches, and you can find out that there are 10 rounds of operation. Okay. So you can count out that, okay, these are my 10 rounds. And if you now go inside this round, you will find out that there are more details you can observe here. Maybe the first part, corresponds to what is called as the sub byte or the S box of your AES computation, followed by some other components. Okay. So you can see that the variations are occurring because, as I said, the power consumption depends upon the underlying data. But the power consumption also depends upon the underlying, not only the operations, but also on the underlying data. Okay. So therefore, if the SPA would have worked, it would have worked because the power consumption depends upon the operations. Okay. Say the S box and maybe the mixed columns. So the S box is the nonlinear part of the cipher. The following part is the mixed column, which is the linear part of the cipher, and they have different power consumption. So if the power consumption would have revealed the secret key, I mean the power consumption variation because of the operations, if it would have revealed the secret key, then that would have been an example of a simple power attack. But for AES and AES kind of ciphers, it is not so straightforward, and therefore you need to kind of resort to a technique which is called as differential power attack, which tries to exploit the fact that the power consumption depends upon the underlying data on which the operations are based on. Okay, and this is an even more powerful form of attack, and that we will try to take a look. So this is an example of a DPA. So for example, DPA on DES, as you can see that with 4,000 power traces, you can, you basically plot something which is called a DPA bias that I will just now explain. And you can see that the DPA bias, right, essentially shows you that whether your secret key that you are guessing, right, is correct or not. So note that you do not guess the entire part of the key, but you try to guess a portion of the key. Okay, so in this case, say I guess only, like a few part of the key, and it shows that this is the correct key because when I'm looking at the DPA bias corresponding to this key, then I get these nice spikes, okay, which I'm not able to observe, in the case of the wrong keys. Okay, so you can see here these guesses are not exposing such kind of spikes, and therefore you basically know that this is the wrong key and the other ones are the correct. I mean, this is the correct key, whereas the other ones are wrong keys. Okay, so you can basically make it work for any algorithm. So this is an example on triple DS, and this is an example of AES, and so on. So let us try to understand before we go into the next topic on why or how you can make a CPA work, or how you can make a differential power attack work. Okay. So any of you who have essentially gone through, like any basic block cipher like AES would be able to connect it. But even for those who are uninitiated, I will try to give a very, quick or very top level, sort of insight into how probably a block cipher would operate. So typically the idea is that in a block cipher, you basically, take a block of data. So imagine that this is your input block. So this could be maybe a 128 bit, it could be a 128 bit input. You take this 128 bit input and you pass it into your cipher. So the cipher is an AES algorithm. And if you give this as the input, then it gives you another block of output. So this is the cipher text, right? This is called as the plain text, and this is the cipher text. And this mapping is done by this cipher. So this cipher is denoted as E, which is the encryption, and there is a small key on which it is operating. So this key is also being fed either externally or maybe it is stored in some kind of non-volatile memory, and using that it performs this translation from plain text to cipher text. So now the attacker is curious and thinks that how it can obtain the secret key. So let us try to look at the attack from the first round. So usually, right, these algorithms are made up of several rounds, like in the famous standard AES. When we talk about AES 128, which means the secret key is of dimension 128 bits. Okay, so it is of 128 bit key length. There are 10 rounds in the encryption process. Okay, so there are 10 individual. How does it do so is shown here in this diagram. So you start with the plain text. So forget the cipher text. So let's start with the plain text. And it tries to do an attack which is a divide and conquer attack, which means it wants to obtain the first round key. So every round has an individual key. The first round is a 128-bit key. So the 128-bit key you can think of, right, essentially is made out of 16 bytes. So now what the attacker does is, rather than obtaining all the 16 bytes together, it tries to focus on one byte of the key. So suppose it tries to obtain this part of the key. It wants to obtain like one component of the key. So therefore, right, what it does is as follows. So it basically takes a, like say it does D amount of encryption. So basically it feeds D plain text. Okay, so let me write this as D. So D could be something like say 1000 plain text. Okay, so imagine that it does 1000 encryptions and it feeds in this D1, D2, D3 and so on till DD. So now note that the attacker wants to obtain this key byte, okay, and this key byte, right, has got some possible values, right? So how many values can a byte take? It can take 256 possible values. So that is shown here as the key hypothesis. So it basically says that there are 256 possible values of this key byte, okay? So now the question is, among these 256 bytes, which one is really possible? The attacker wants to know out of these 256 possible values of the key, which one is the correct key byte. So therefore, what the attacker now does is it takes the first input, say D1, it makes a guess on the key hypothesis. Say, let me assume that the first key hypothesis is 0. So it assumes that the key byte is 0. And it does the first round of encryption, which is nothing but in this case, but just by like doing an XOR operation and then doing a table lookup, and then it comes to this output of this first round and notes them in a table. So this therefore you can observe that this byte, if it is like operated on this byte, will give you another byte which is stored over here. Next, what you do is you go into the next byte, and again you work with this key hypothesis of 0, and you get the next possible thing which is stored over here. So like this, right, if there are D such possible inputs, you get D such bytes for this initial key hypothesis of 0. Okay, so that means once I have guessed 0, for 0, I have got this entire column. Now I want to know that whether my guess is correct or not. So in order to do that, what I do is a very simple thing. Okay, so what I do now is I apply a powered model. So this powered model could be a simple Hamming weight powered model, which means that it takes this byte and replaces it by its corresponding Hamming weight. So Hamming weight of a byte means that it corresponds to the number of ones in that byte. So for instance, like if I've got a byte like 1100, okay, and maybe 0101, then the Hamming weight of this will correspond to 2 plus 2, that is 4. Okay, so the Hamming weight, as you can understand, for a byte can range from 0 to 8. There are possible 9 Hamming classes that can occur for a given byte. So therefore it replaces this byte by this value, and likewise it replaces it for the entire column, and it has got essentially this column, which is called as the hypothetical power consumption. So why is they are called as hypothetical power consumption? They are called as hypothetical power consumption because in VLSI there is this notion that the power consumption of a device, right, of a byte, I mean when it is doing its computation, and you want to kind of get an estimate of how much will be the power consumption, then you apply these power models. Okay, and these power models could be varying from simple power models to more complex power models. One of the simplest power models is what is called as a Hamming weight power model, which means that if there is an internal register on which you are storing the data, so try to find out what is the Hamming weight of this device, of this register. If the Hamming weight is more, then it will probably lead to more power consumption. If the Hamming weight is less, then probably it will lead to less power consumption. So therefore, what you do now is that you basically replace these bytes that you have calculated based upon the input and your key hypothesis that you have made, and you obtain a hypothetical vector. Okay, and now note that since you have got the actual power trace, you also have got the real life power vector. Okay, and then what you do, and note that these real life vectors, right, you have not only observed at one time instance, but maybe at t time instances. So now what you do is that if you are now, remember that you have made this key hypothesis 0, and you want to know that whether this hypothesis is correct or not. So what you do is you take this hypothetical power and you try to correlate with all these possible observations that you have done. If the correlation is strong, that means if you get a high correlation, then there is a chance that this key hypothesis was probably correct. But if you find that none of these correlations is strong, then you discard this case. You go into your next case. Okay. Actually, you can essentially perform all these possible, like hypotheses, because these are only say 256 possible values, and for all of them, right, you basically plot the corresponding, like correlations. So how do you plot them? You can have different ways, but one very simple and convenient way is to form this matrix, which is called as correlation matrix. Okay. So in this correlation matrix, every row corresponds to a key hypothesis, and every column corresponds to a time instance. Okay. And you find that for a given key hypothesis, if you find that there is one location in that row where there is a strong correlation, then you possibly keep that or keep those rows as candidate keys, whereas the ones for which all of the entries are low, you discard them. Okay. So for a certain amount of observations, you find that gradually your number of possibilities would reduce, and since it's a statistical process, if you have more and more observations, then finally you will be left with only one single row, and that corresponds to your key hypothesis. Okay. So you see that in a divide and conquer manner, you are able to obtain the key hypothesis, and this you can apply in parallel to all the 16 bytes, and hence recover the key in a much faster time. Okay. And this is basically the basic principle of correlation power attack. And I would be curious to know if there are any questions on this discussion. So I would say that this is one of the most important part of my talk here, and if there are some questions, then I would be happy to address on this.
Participants, please, if you have any question.
Okay, so I believe that you get the idea that the CPI is a divide and conquer attack, which means that although my key complexity, right, of an AES kind of algorithm was 2 to the power of 128, but now I have reduced my effort to obtain 1 byte of the key to only 2 power of 8 values. Okay, because I just need to make 256 guesses, and this I can do 1 by 1 for all the other bytes, and therefore my total complexity will be 16 multiplied by 2 to the power of 8, whereas in my previous case it was 2 to the power of 8 to the power of 16. Okay, so that essentially is why you have got a very significant reduction in the complexity, and that is why you have got a very efficient attack methodology. Okay. So this is the basic principle of the attack, and one of the things that we try to do in our laboratory is to build an open source platform. We also have a startup which we call as ESP, through which we try to commercialize this tool at a much lesser cost compared to, we try to build a low cost tool for evaluation and experimentation. So this brings me to the next part of my talk, which is essentially a fault attack. So essentially trying to kind of stress why fault tolerance is so important in the context of cryptography. So when we talk about these kind of attack vectors, so these attack vectors are abbreviated as DFA, or differential fault attacks. So differential fault attacks essentially means that you take a plain text and you apply an encryption algorithm, you get a fault-free cipher. Next time when you want to do an encryption, you try to kind of do some kind of fault injection, and the fault injection results in a faulty ciphertext. So the issue is that, or the question is that, whether analyzing the fault-free cipher and the faulty cipher, you can do an analysis which will leak the secret key. So let us try to take a very quick insight into this by again considering the AES algorithm. So in AES, right, and I will be considering the last 3 rounds of AES, basically the 8th round and the 9th round and the 10th round of AES 128. So imagine that because of some kind of perturbation that you do, maybe like a glitch in the clock line, or maybe a fluctuation in the voltage line, or maybe by using some more sophisticated instruments like an electromagnetic radiation, maybe by a laser gun, somehow, right, you create a perturbation so that one of the bytes inside your cipher gets corrupted by some random fault. So random fault means it's an arbitrary value, and I've got no knowledge as an attacker about what this fault is. So then if like allow the fault to propagate in your cipher, you will find that, and if you analyze them, then at least in most of the ciphers, even in the without loss of generality in the case of AES, you will find that it starts exhibiting nice interrelationships. For example, if you observe, like the outcome at the output of this step, that is the 9th round mixed column, you will find out that there are very nice interrelationships between the bytes. Okay, these relationships are in the Galois math on which the AES is built on, but you can see that, for example, this byte is twice this byte is the same as this byte is thrice as this byte, and so on. So as an attacker, what you can now do is you can now try to go ahead and get the cipher, and then you try to work behind by guessing the portions of the key, and then trying to see that whether these equations are being maintained for your guesses. That way, you can essentially develop a filter which can remove the wrong cases from the correct cases. Okay? That is the basic idea behind fault analysis of ciphers, and it is a very powerful form of attacks, because you can see that, just to give you a summary, that a single fault, that means only one fault, can reduce the AES key size from 2 to the power of 128 possibilities to only 256 values. Okay, and the key conjuring will take something like 2 to the power of 30 trials. So you can see that it will take less than 15 minutes or so, you can get the entire 128-bit secret key in a matter of flash. Okay, so therefore, right, people have been studying these fault injections in various contexts. So I will try to talk about an experiment specifically in the context of automotive chips, because remember I started to say that automotives are very important, the security aspects in automotives are growingly important topics of discussion. And while, like in automotive chips designs, there are certain standards which are essentially based upon reliability and safety. And there is a framework called as ISO 26262, which is a framework for safe automotive electronic systems. And they try to develop what are called as ASIL, or automotive security integrity levels, marking them from level A to level D. The idea being that when you go into level D chips, then they are extremely safe. But let me try to talk about an example which shows that even if I take an ASIL D chip, it can be subjected to fault attacks, and therefore again it like reiterates the point that safety and security are not the same. So in this particular example, we take two ASIL D chips, ASIL D1 and ASIL D2 chips. The first one is an ARM Cortex R4 core. The second one is a PowerPC. Both of them are very prevalent architectures in the safety electronic industry. Okay, and we subject them to two fault injection mechanisms. The first one is a voltage glitcher. The second one is essentially an electromagnetic glitcher. Okay, and we have essentially such kind of setups in our laboratory, through which essentially you can like try to induce internal faults inside your circuit. So let us try to talk about a very simple exercise or experiment that we can do. The first experiment says that you perform some assembly level code in your chip, which basically counts up, and then you basically try to see that whether all the instructions are being performed. The idea being is that if you are injecting a fault, then one of these instructions can get skipped, and therefore, right, you will not get the requisite amount of output. That means probably you have, if you want to kind of count up, say 10 times or 20 times, then probably you will get a value which is less than 10 or less than 20. The second experiment is where the chip has got a JTAG port, and you basically create a kind of if statement in the code that is getting executed on the microcontroller, and you want to ensure that the access to the JTAG is only ensured when you give the correct password, okay, or maybe you essentially are authenticated. So the idea being is that now when you are entering the fault, and the objective of the fault would be to bypass this check, and so that it goes on, like to your and gives you the access to the JTAG by injecting the fault. So this is an experiment that was being done. The first case is this unrolling of an assembly instruction. We call that as an unrolled experiment. The second one is an authentication experiment. So we found out that in the ASIL D1 chip, the report says that you have got, when you are doing voltage injection, then 87% of the time it is unable to detect. It basically doesn't throw any alarm, but the output is wrong, which means that the chip is exhibiting or exposing a wrong output and is not really understanding that there is a fault attack or fault being injected. In the second case, when you are doing an EM-based attack, then the acidity to chip, that is the second one, essentially shows that 57% of the time there is a compromise. So this shows us that the inherent security mechanism fails. So let us try to talk about a postmortem that we basically did, and we found out that the safety mechanism that is being inbuilt inside this chip is based upon a time redundancy check, which means that it does the computation twice and it tries to compare the results, and if one of the computation is faulted, then you basically throw an alarm. But then these fault injections are essentially bypassing the detection mechanism, because the way the fault detection is probably being done is by like implementing a three-stage pipeline, and the idea being is that every instruction is performed once and again subsequent to that, to ensure that the computations are same in both the successive instructions. But then the idea, but what happens here is that when you're injecting the fault, then the fault, so imagine that your instruction one is at the third stage of the pipeline, and the second instruction, again, when you are repeating it and you are trying to incorporate redundancy, you are bringing that in the pipeline, and that is, say, in the first stage of the pipeline. So when you're injecting the fault essentially is affecting both the instructions simultaneously, and because both of them are co-deciding at the same timestamp in the pipeline, and therefore the fault is essentially kind of affecting both of them in the same manner. And since it is happening in that manner, when you are comparing, you are finding that both of them essentially have got the same result, and therefore irrespective of the fault, it is bypassed and is not being detected by the redundancy check. Okay, so this shows us that and this is just a postmortem because we do not have accurate information, but it kind of tells us that there is a good chance that the fault can be missed because of the fact that when you're injecting the fault, then you are ensuring that you're basically, as an attacker, you are able to bias your fault injection, and this leads to a significant enhancement in the probability of your like bypassing the countermeasures. So this tells us that safety and security are not the same, and therefore we need a suitable strategy. So before I go into the next part, and just to give you kind of an illustration, so I will just would like to show you this video of a demonstration on possible side channel tool. Hopefully it works. So can you listen to the sound? Please just let me know.
Sound is not coming, sir.
Sound is coming,
No, sir.
but you can see it, right?
Yes. Just for a second,
click on play.
Sorry.
Just for a second, some sound came in.
Are you able to hear the sound? No.
No, sir.
No, sir.
Okay. Okay, so I think the sound is probably not allowed probably.
If you would have these WebEx apps, then there is a option of selecting sound and all.
This is from the WebEx app only I'm showing. I don't know why it's not coming.
So when you are sharing now, sir, you see on the right corner, there is a sound symbol of speaker. Okay. And there's a drop down option over there. You can choose optimize motion and video.
Yeah, so you can see my screen, right?
No, right now not visible. I cannot see.
Okay. Can you listen now?
Yes, sir. Yes.
setup. So you can see here that when the fault is injected, this value changes. Okay, so this is an illustration of So this is just an overview of some of the side channel experiments. Essentially, I had been talking. So that brings me to the next part of my presentation, where essentially we talk about like this security privacy aspects in context to IoT. So we know that the IoT essentially are resource constrained, and therefore it brings us to the question that whether we can develop lightweight solutions for security. So in this IEEE design and test paper in 2016, I tried to publish a work where we showed that how a new hardware security primitive, which is called as physically unclonable function, can work as promising tools for security. So let us try to understand what puffs mean. And before I go into that, let me talk about the glaring security weakness in authentication mechanism of, again, the Philips Hue lighting system. So in one of these experiments that we found out is that the idea is that the Philips lighting systems are basically smart bulbs. So which means that these bulbs have got the power of control and command, and they connect with a switch. The idea is that you essentially as a user are whitelisted to control and command those bulbs, but the objective is that your neighbor who is not whitelisted should not be able to control and command those bulbs. But imagine that if your neighbor is able to break the authentication requirements, then he or she, right, can control and command the bulbs at his or her will, which is not really desirable. So we found out that initially in the authentication mechanism of these lighting systems, the idea was that when the app was launched, the hashed value of the MAC address of the device was used to create the username, and it was whitelisted in the breach. And if the attacker knows the MAC address of the device, there are several ways of knowing the MAC address, and the hash function being a public hash function, it was the MD5 hash at that time, the attacker can essentially obtain the whitelist and therefore easily control and command those bulbs. Later on, this mechanism was changed, but it became even more worse. So what it became was that, so this is an experiment that one can do in the lab. So you can see that when the username is created and at the time of registration, there is a username that is being generated, and there is a random number that essentially is obtained, and the random number is subsequently communicated, and the random number can be also picked up by standard eavesdropping tools like Wireshark and so on, and this basically leads to the fetching of the username. So you can see that this particular second snapshot shows that while sending any command to the breach, the username is fetched by the Wireshark tool, and using this, the IP address of the breach and the username, the entire whitelist of the breach can get exposed. Okay, so this shows that these mechanisms have glaringly bad authentication mechanisms, and one of the reasons is not that people are unaware of how to protect their systems by applying suitable cryptographic techniques, but the fact is that most of these cryptographic techniques are very costly. So therefore, right, this motivates us to study and develop techniques which are lightweight and still which lead to security. So this brings us to this nice hardware primitive which is called as puff, and I will try to explain what puffs mean subsequent to this. Okay, so therefore, right, puffs, simply put, essentially means that it is kind of, you can think of a very like a holy grail device. So it is basically working like as a fingerprint of the electronic circuit. Okay, so that means like once you take the puff, and if you take the puff and put it into several chips, then each of these chips, right, that you have, like maybe chip 1, chip 2, and chip 3, and if you take the same challenge, and if you apply to all of them, the responses that you get from each of these, right, are statistically independent. That means if I tell you the response of one of the device, and I tell you like what is the response of the other device, you have got no clue. Responses have to be unpredictable. Okay, and also the device has to kind of resist against I mean, you can imagine that each of the device essentially has to be unique. That means, like the knowledge of this response should be kind of distinct from the response of the other. Additionally, these devices, right, always are exposing the inputs and the outputs, which we call as challenges and responses. So therefore, it should be resistant against machine learning attacks, okay, or model building attacks, because the model building or the machine learning tools are very smart and getting smarter. And therefore, right, if you give access to the inputs and outputs, and if the machine learning tool is able to tell you the mathematical model or the physical model seems more difficult, then the entire security guarantees will collapse. So the reasons why the puffs work or should work is basically kind of dependent upon the underlying physics. Okay, and in a very top level manner, it's like a Boolean function or a Boolean mapping. If I give an input the challenge, the output is the response. But the response to the challenge mapping is not mathematical. So it is not like it is implementing a mathematical function, but rather it is a circuit which is dependent upon the underlying device physics. Okay, and in the device, right, there can be several reasons why this uncertainty will happen. So that it is because of the CMOS scaling, for which there will be like variations in the MOS device's physical parameters, which will lead to the overall like maybe variations leakage current, design such systems, and whether you can use them in your protocols, and whether you get an end-to-end security. So here is a very simple experiment that one can do in your lab. So it's an example of a ring oscillator, which is a very popular digital circuit, and you try to implement them in several FPGA devices. Okay, so here we say we take a 3-stage ring oscillator and we implement them in say 4 FPGAs as shown over here, and you will find the oscillating frequency of the ring oscillator is dependent upon the device. Okay, so for example, here you can see that the average oscillation frequency is around say 135, whereas in this FPGA2 it is around say 122. So you can see that the same circuit, right, essentially when you're implementing on two devices has got slightly different behavior. Okay, and this essentially tells us that potentially you can use this device unique behavior to develop device fingerprints, and using that you can do an identification and key establishment like in a very simple manner for the devices. So therefore, right, the advantages of puffs are it will reduce cost and it will raise security. If you compare a world without puff and a world with puff, you can see that there are many advantages that a puff can bring in. For example, there is no really a key being stored in some kind of non-volatile memory, which you will probably do in a world without puff, and that is often subjected to sidechain attacks and several other possible attack avenues. Okay. So, but in the world with puff, the key never leaves the IC's cryptographic boundary. It is not stored in a non-volatile memory. Rather, the entire device starts to operate as the key. The key is deleted. Basically, it's not there. Okay, it's not present in any like 0-1 string stored in some form of memory. So therefore, right, I mean, it seems to be very sort of promising, and therefore, right, around the world, there has been several efforts of designing suitable quality metrics for the puff. So the two most popular metrics are, as I mentioned, is one of them is uniqueness, which means that each of the devices should be statistically producing a statistically independent output. And the other important aspect is also reliability, because you see that there is another like concept we are called as true random number generators. So if you compare it with puffs, one of the important requirement of a puff is that if I apply the same challenge, it should produce me or provide me the same response, whereas across devices I should get randomness. Okay, so therefore if I take one device, and what I want is reliability, because I want that even if say the ambient temperature changes, the humidity changes, or the environment changes, still, right, the behavior should not be ad hoc and should not be arbitrary. Okay, so I want randomness on one end from across devices, but what I want is inside that device or intra that device there should be less amount of variation, and the variation should be more controlled. So that makes the design principle of puffs very, very complicated and very, very challenging. And but however, if you imagine that if you have such a puff, right, then you can apply it for authentication. So here in this diagram or in this slide, we try to illustrate a classic application of puff for scenario. So imagine that there is a device, say this device which has got a puff, So the path essentially is embedded in this device, and you can apply a challenge and you can obtain the response of the path, and you are questioning that whether the device is authentic. So now if you look at the server end, so imagine that this is a client node and this is a server. The server doesn't have a copy of the path because the path by definition is unclonable. So what you can do best is, at best, you can have a challenge response table. And classically, right, what you do is you basically have a challenge response table, and where you store, say, like certain number of challenges and their corresponding responses. So now what you do is you take one of these challenges as a verifying agency, you basically send the challenge and you obtain the response, and then you do a match. If you find that this output matches with your database, then you allow that device to get access, else you stop that access. Okay. So note that since the attacker is also seeing the challenge in the responses, you cannot reuse the challenge in the response, and therefore once you use the challenge, you have to struck it off. Okay. So this means that your challenge space should be sufficiently large, and while you are accessing the challenges and the responses, the attacker should not be able to apply some kind of machine learning or model building to build a mathematical clone of the path. Okay. So these kind of puffs are typically called as strong puffs, where you essentially the puff has got a very large challenge space. Typically, it's a 64-bit or more than that, which means there are 2 to the power of 64 possible challenges, and still, right, the puff is resistant against model building or machine learning. So therefore, right, but there is a problem in this naive authentication. As you can observe, probably that you need to store the CRP explicitly in the verifier agency, and therefore, right, that can be a point of contact or point of like a point or can provide an attack surface to the adversary. Okay. So therefore, in one of our projects, we had a problem of trying to develop a path-based authentication protocol, which doesn't explicitly store the challenge response mapping in a sort of table. So in this particular protocol, what is done is that there is an enrollment phase. So imagine that there is a device that you want to like connect in an IoT kind of system. So you take this device, which essentially is embedded with the path. So there is a path, okay, and you want to enroll it to a security credential generator. So what the security credential does is basically it sends a challenge and obtains a response, and then it applies a hash function, which is a typical cryptographic hash function, and obtains an output, say, called as PA. Okay, and then it knows that this device will, say, communicate with a verifier. Okay, and the verifier has got, since it's a verifier, it can be a server. So it's a heterogeneous IoT kind of typical system. So it basically has a memory in which the verifier has got a secret key, and I call that as case. Okay. So now what I do is I take this another randomly generated input, which is, say, called CS. You apply along with this case which the verifier has, and you apply a hash function and obtain something which is called as PS. So now you take this PA and PS and you apply an elliptic curve operation, which is shown over here by generating a random scalar called as A, and you calculate a parameter which is called as B. The key takeaway from this slide is, rather without going into too much details, is that you can calculate these parameters like which are shown here as CA, CS, A, and B, and you can store in the cloud. Okay. So now note that since you are storing in the cloud, you have the attacker also can see this information, but can the attacker obtain the responses of the path? So you can see here that in order to obtain, say, PA, okay, it basically needs to obtain the response and obtain PA. So the attacker is not really storing PA over in the network. So it is not really storing the, really not storing the exact input, but it is storing a kind of hashed response of the corresponding thing. Okay. Likewise, you can also observe that there is this secret scalar A, and through which it is doing an elliptic curve operation, and it is not explicitly storing, the information which essentially reveals the internal data. So, but rather it basically stores the kind of modified information, and that is essentially stored in the cloud. So how this information can be leveraged to do an authentication is showed here in the next step, where we are interested about going in the verification phase. So now when you are, so you note that when you are interested, like so what you have stored in the cloud is this input CA,
and he has stored this input CS. Okay, so the idea being that in order to get RA, the attacker needs access to this path, because only the path can map this CA to RA, and there is no other model through which you can get this mapping. Okay, and this is being leveraged in the verification phase, where you essentially have, suppose this node wants to communicate with this verifier. So what the verifier does now is the verifier accesses the cloud and gets this tuple CA, CS, A and B. And now note that the verifier has got the secret key case. So what it does is it applies the hash function, gets this PS, and applies the opposite of the elliptic curve operation and computes A into PS plus B to get the value of PA. So note that PA was nothing but the hash of the response. Okay, so PA was nothing but the hash of the response. So therefore now what the verifier can do now, the verifier can create a like an input challenge called as QA by applying some kind of formulation by generating a random X, and it expects a corresponding response to that. So now what it does is basically sends this challenge to the node, and the node can respond to it, because the node essentially can, since it has got access to the path, it can compute the value of PA directly by applying the hash function on the output of the path, and then it can obtain out this PS dash which is needed to compute out this parameter called as VA dash. So the idea of this VA dash is nothing but it's a response of the challenge that has been provided to this node. So then once this response comes back, the verifier basically checks that whether this is correct, and if it is so, then the node is allowed access. Okay, so one of the key points behind this protocol is that we are never storing explicitly the challenge response in the verifier end, but the verifier performs an authentication by applying an elliptic curve operation which is dependent upon its own secret key. So this work was jointly developed with a company, and we tried to develop with Wipro, and where we did a technology transfer of this idea so that our IoT systems can be potentially developed with these kind of safeguards. So here is a demonstration of that on a video surveillance camera, which you see everywhere. And most of these video surveillance cameras essentially have got security weaknesses. So in one of the attacks, we showed that how a meet in the middle attack can be done, which means that there is a man sitting in the middle who tries to kind of play stale video, that means old video, and can confuse the at the receiver end. So we try to kind of fortify the system by having this path-based mechanism. So now when the the criminal in the middle tries to say play a stale packet, it is unable to do so, because it cannot respond in the exactly the same way as my legitimate endpoint or the legitimate node, because simply because the man in the middle doesn't have access to this path. Okay, and since it doesn't have access to the path, it doesn't have access to the required information which is required in the authentication protocol. Okay, so there are formal proofs of security and so on, which is detailed in this IEEE TDSC paper, which I'm not going in details. So finally, right, we also do a detailed analysis to ensure that the power budget and the other resources are properly mitigated. The overall latency of this protocol is around 480 milliseconds. So, and it is implemented on a 512-bit prime, which is as per the standard specification of an elliptic curve. So finally, right, I mean, we also sort of use this path and apply it for preventing another very popular attack on a wireless protocol, which is called as WP82. And I will just try to play this. Hopefully you can hear it. just a demonstration of showing you that how an authentication can work in the context of a system which is built around puff, and not only like it gets lightweightness, but also it helps to prevent this powerful class of man in the middle attacks. Okay, so I will rather be a little quick because I think I'm running out of time. So and come up just talk briefly about the last point that I wanted to touch upon, which is on the context of the privacy in the context of cloud. So one of the key points here is, like you have got information in the cloud, and how do you really ensure that your data is secure? That is, your data is not being accessed by any other third party. So of course, like what you want to do, say you want to build a system where, suppose you want to do a searchable encryption, which means you want to ensure that your data is there in the cloud, and you basically allow it to, be stay secured by doing a wrapper of encryption. But in one of these popular searchable encryptions, they quietly write this line. If you look into details, like it says, like, to provide you with the most relevant search results, we then decrypt your search engine search term and securely request results from our search and content partners. So which means the server is able to learn, okay, and that is exactly what we don't want. So we want that the information should be there on the cloud in an encrypted fashion, but still I will be able to, as a client, to do my search operations, but the server should not learn anything about the data or should not learn anything about what I'm trying to search. So these are called as typically privacy enabled search, and there are various techniques which people have been looking into. On one end, you have got techniques which are very secured, which are called as like fully homomorphic encryption and so on. On the other hand, there are techniques which are more efficient, like property preserving encryptions and so on, but they are not very secure. So we try to take a middle path, which is essentially trying to look into this technology, which is called as searchable encryption. Okay, and we are trying to kind of develop solutions which essentially provide us a reasonable trade-off between security and efficiency, but still allow us to do some basic search and other operations. So in the very top level, what we want to do is we want to ensure that the data is, because remember that in an IoT system or in a cyber physical system, there are so much amount of information which is being put into the cloud. It could be your medical data and so on, and you want to ensure that the data is there in the cloud and is in an encrypted fashion. But if you want to do, say, a search operation, say I want to, say, run a query which is essentially as shown here, like return all emails with Alice as recipient and Bob as sender and with crypto and in the subject. So if you think about an encrypted email service, then you essentially will not be able to do that if the data is encrypted, because the moment you do encryption, it becomes kind of random, right? And you are not able to kind of do such kind of operations. On the contrary, right, there are certain techniques that people are working on, and we are also trying to work in that direction of trying to develop methodologies through which you can essentially do some, some operations like search, or maybe more specifically conjunctive search and so on. So I will not again go into the details because I think I'm running really bad out of the time, but I will stop by showing you this quick demonstration of what I'm trying to kind of hint at. Okay. Okay, so basically, like we are trying to see that whether this basic infrastructure on searchable encryption can be made even more efficient by applying parallelisms and like using special purpose hardware or FPGA accelerations to ensure that the overall search can be really accelerated. And there are many other directions that we are trying to look at. One of the things that, as I mentioned, is in the context of like because being in India, we often buy several components from foreign source, and therefore there is always this sort of question on whether our designs are trusted. So as I mentioned, one of the things that we are trying to look into is whether you can use imaging-based techniques for diagnosing and understanding whether there are any infections in your present implementations. So we are one of the things that we have set up or setting up in our institute is what is called as an SEM and FIB. So you can see that this is a small chip and a MEMS chip, and on the right hand side you can see an antenna. So you can see the amount of magnification that has been done, which is impossible to see with open eyes. And we are trying to see whether you can have a systematic technique or mechanism of obtaining these images and then doing image processing, machine learning, and so on to develop an in-house flow for an imaging-based Trojan detection. So so basically, like the other thing while we are working on searchable encryptions, the other important question is on the domain of what are called as fully homomorphic encryption. So we are trying to see whether we can design and implement leakage resilient, concretely efficient, quantum resistant, fully homomorphic encryptions and realize them for practical applications. So to conclude, security of IoT is of utmost importance in the modern society, and IoT provides us with like various endpoints, starting from resource constrained endpoints to more powerful endpoints, and there are different attack surfaces that we need to kind of investigate. We strive to develop novel tools and solutions for side channel security, designing new hardware primitives for end-to-end IoT security. Finally, as a chain is no stronger than its weakest link, it is important as a society to work in all these verticals and try to ensure that we collaborate together so that we have a more, like holistic security. So if you're interested, there is this workshop that we do every year in India, what is called as Space 2021. This year it's being done virtually. There are very exciting talks that are going to be present. So I would encourage or invite you to please participate in this event. And if there are any questions, I would be happy to answer. So that brings me to the end of my talk. Thank you for your attention.
Participants, do you have any question?
Sir, good evening, sir.
Yeah, good evening.
Sir, thanks a lot, sir. First of all, I learned a lot with this session. Sir, what are the famous mathematical methods for physical unclonable functions? Are there any famous mathematical methods for physical unclonable functions?
Famous mathematical method. You mean to say like design techniques for puffs, right?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Yeah, so there are different types of puffs, and there are, for example, right, there are like
In challenge response systems, sir. In challenge response systems.
yeah, so there are like if you, I think the starting point for learning puffs would be something which is called as an like arbiter puff. Okay, so the arbiter puff is based upon a cascade of crossbar switches, and which ends with a D flip flop. Okay, so this is the basic structure, or at least one of the most primitive structures of a puff or a delay based puff, to be more specific. But there has been very interesting machine learning attacks on this structure. So people have shown how you can like build very powerful model building attacks with almost like 99% accuracy by seeing the challenges and its corresponding responses. And therefore, in order to prevent it, people have come up with more protections and secured mechanisms of puff designs so that they are like they can withstand such kind of machine learning attacks. Some of those examples I would say, like if you are noting down, is this there are techniques we are called as like For example, in one of our works, we did develop an attack which is called as a multiplexer puff or a mux puff. Okay, there is a technique which is called as an XOR puff, which basically takes these puffs, arbiter puffs, and does an XORing. And there is a theory which says that if there are more than 6 XORs, then it is very hard to do machine learning attacks, at least the straightforward machine learning attacks. And then there are many other like puff variants actually. Once you get into the literature, I believe you will find more insights. If you are interested, then we have a book on hardware security written by me and another colleague of mine, Professor Rajat. You can find more details in one, at least an introductory chapter, where you can find some initial discussions and like other designs on puffs.
Thank you, sir. Thank you.
Anybody else? Okay, I think nobody has any question more. So thank you, sir, for giving your time for this session. And your session was very detailed and very good actually. Students have learned many things from your session. So we are thankful to you for your
Thank you so much.
beautiful session. Again,
Thank you.
Thank you, sir.
Bye-bye.
So dear participants, so today we end here. Thank you for attending all the sessions nicely and patiently. So you will learn many things from these sessions because most of the speakers, that they are from renowned institutes and they are dedicatedly like working those specific fields of this the fields we are talking about in this FDP. So tomorrow we'll assemble again in this virtual platform. So thank you for today.
Thank you, sir.